Welcome back to the lecture hall, everyone, and thank you for joining me today. Please take your seats. Today, we are opening a brand new, highly intricate, and deeply fascinating chapter in our watchmaking theory course, Chapter 9, which covers calendar mechanisms in mechanical watches. Up until this point in our studies, we have focused primarily on the continuous, unbroken flow of time hours, minutes, and seconds and how to power that flow through manual gear trains or automatic winding rotors. But today, we are asking our mechanical movement to perform a completely different, almost mathematical task. We are asking it to become a calendar. Take a look at the title slide on the screen. What exactly is a calendar watch complication? By definition, it is an intricate mechanical system integrated into a base timepiece that calculates and displays the date, the day of the week, the month, and often the celestial phases of the moon. And here is the most crucial engineering constraint you must understand from day one: this entire secondary calendar system possesses absolutely no independent power source of its own. It is driven entirely by siphoning parasitic energy from the base timekeeping gear train. Over the course of this 6-part lecture series, we will deconstruct everything from the simplest date wheels to the awe-inspiring perpetual calendars that automatically calculate leap years. Here in Part 1, we will lay the historical and mathematical foundation. We will explore the historical evolution of calendar watches, define the basic indication paradigms, and dissect the strict mathematical gear ratios required to step down the fast rotation of the hour hands into the slow, deliberate, daily jump of a date wheel. Let's begin. Before we dive directly into the spinning gears and jumper springs, let's take a look at the horologist's archival blueprint on the screen to establish our Chapter 9 roadmap. As you can clearly see from the schematic, this chapter is massive. It is divided into 7 distinct technical sections, ranging from 9.1 to 9.7. To make this volume of information digestible, we have broken the chapter down into 6 progressive lecture modules. Currently, we are in Module 1. Our primary focus today will be on Section 9.1, covering the general principles, the etymology, and the rich history of calendar watches. This will give us the essential context and terminology we need to communicate like professional watchmakers. Following that, we will transition into Section 9.2.1, where we tackle the infamous 1-to-2 reduction ratio. This is where we establish the fundamental 24-hour kinematic constraint, meaning how we physically force a rapidly moving gear to turn exactly 1 time per day. Looking ahead to our future modules, Part 2 will cover the actual kinematics of the date changeover, comparing the trailing, semi-instantaneous, and instantaneous mechanisms, along with critical safety devices designed to prevent users from breaking their watches. Part 3 will apply these mechanical rules to the day of the week and month indications, as well as introducing the basic star wheel moon phase. In Part 4, we will look at high-precision gear train moon phases and assemble all these components into the complete simple calendar module. Finally, Parts 5 and 6 will be dedicated exclusively to the crown jewel of horology, the Perpetual calendar, exploring both the 48-cam and 12-cam architectures in painstaking detail. Today is about setting the absolute baseline, so let's move to our first core concept. To truly master Swiss watchmaking theory, we must speak the language of the original master watchmakers. Let's look at the etymology of 2 fundamental French terms you will encounter daily in horological literature: calendrier and quantime. Please direct your attention to the comparison matrix on the screen. On the left, we have calendrier, or calendar. This word originates from the Latin verb calare, which translates directly to call or to proclaim. In ancient Rome, the first day of every single month was known as the calend. On this specific day, citizens were formally summoned by priests to the public square to hear the official announcements for upcoming religious feast days and civic events. In modern horology, when we use the term montre calendrier, we are referring to a broader, more comprehensive system of time division. It implies a watch that encompasses seasons, months, weeks, and astronomical phenomena like moon phases and tides. On the right side of the matrix, we have the term quantime, which translates simply to date. This comes from the Latin word quantum, meaning how much or what number. Historically, it asked the specific numerical question: what is the precise numerical date of the month today? Therefore, a montre à quantimes strictly designates the specific mechanical counting of numerical days. However, as language, culture, and marketing have evolved over the centuries, modern horology uses both terms almost interchangeably. Whether a Swiss brand calls their flagship timepiece a quantime perpetual or a perpetual calendar, they are referring to the exact same highly complex mechanical complication. Now, let's trace the horological evolution timeline of these calendar watches. Look at the timeline stretching across the screen. It is a very common historical misconception that the calendar watch was suddenly invented on a specific date by a single genius. Rather, it was a gradual, painstaking evolution of mechanical miniaturization spanning several centuries. In the 16th century, massive astronomical clocks were already being built for town squares and towering cathedrals across Europe. These giant, room-sized machines served as the theoretical foundation of mechanical calendars. By the mid-17th century, master watchmakers attempted to shrink these massive gear trains into portable pocket formats. A prime historical example is the stunning oval astronomical watch signed by Marc-Gerard Aubois, which you can see in the diagram. This incredible 17th century artifact didn't just tell the hours, it featured symbolic, engraved figures for the days of the week, tracked the lunar phases, the dates, and the months. It was a masterpiece of early micro-engineering. As we move into the late 18th century, calendar pocket watches finally entered regular, albeit highly exclusive, production for European aristocracy. The absolute apex of this era was the year 1827, with the completion of the legendary Marie Antoinette pocket watch by the master himself, Abraham Louis Breguet. It featured a perpetual calendar, equation of time, and a minute repeater inside a transparent rock crystal dial. Finally, it wasn't until the early 20th century that the modern calendar wristwatch emerged. Engineers successfully miniaturized and, crucially, shock-proofed these delicate calendar complications so they could survive the violent daily movements of the human wrist. During the centuries-long historical evolution, the Swiss watchmaking industry developed a very specific, standardized terminology to categorize the sheer volume of information a watch displayed. Look at the categorization matrix on the screen. By the late 18th century, these French terms were the absolute standard for describing calendar complexity, and they are still used in patent filings today. On the far left, we have the montre à un quantime, which translates to a watch with exactly one date indicator. This is your standard, everyday date watch. Its display and mechanism are designed to indicate only the numerical day of the month, sweeping from 1 to 31. In the middle, we step up in mechanical complexity to the montre à deux quantimes. This designates a timepiece that indicates two distinct pieces of calendar data simultaneously, the numerical date and the day of the week. Today, in modern collector terminology, we commonly refer to this as a day-date complication. Mechanically, it adds a 7-tooth star system to the baseline date architecture. Finally, on the right, we reach the prestigious montre à trois quantimes, or the triple calendar. This highly complex mechanism integrates multiple gear trains to indicate the numerical date, the day of the week, and the month of the year. If you recall the Marie Antoinette watch by Breguet that we discussed on the previous slide, it was the ultimate, transcendent expression of this concept, taking the three quantimes and engineering them to be perpetual, meaning it never needed manual adjustment. Understanding this historical nomenclature is vital for reading traditional Swiss technical blueprints. Now that we understand the deep history and the terminology, let's look at how this calendar information is actually presented to the wearer on the dial. There are two fundamental display paradigms in calendar horology. Paradigm 1 is the aiguille, which is the French term for a hand or pointer indication. In this deeply classic, traditional approach, physical hands are press-fitted directly onto the arbors of the underlying rotating star wheels. These hands sweep across dedicated subsidiary dials or point to numbers along the main dial's outer perimeter. Paradigm 2 is the disc, or the disc indication. This is the modern standard for legibility. Here, flat numerical rings or printed plates rotate entirely hidden beneath the main dial. The wearer only sees the current, relevant data through precise, small cutouts in the dial face, which we call guichets or aperture windows. However, I need you to focus on the red warning box at the bottom of the screen. Regardless of whether the watchmaker chooses the aiguille hand paradigm or the disc aperture paradigm, there is one absolute, non-negotiable kinematic rule that every single calendar mechanism must obey: the underlying driving source must be engineered so that the physical indicator advances exactly one time every 24 hours. The entire mechanical engineering challenge of the simple calendar is taking the fast, continuous rotary motion of the timekeeping gears and mathematically slowing it down to produce one single, discrete, satisfying mechanical jump exactly at midnight. This strict 24-hour constraint dictates all the gear ratios we are about to discuss. Let's take a much deeper dive into Paradigm 1, the aiguille, or hand indication. Please look at the mechanical profile cutaway and the dial architectures on the screen to understand how this is physically constructed. Mechanically, this system requires a direct, vertical physical connection. The indicating needle, the hand, is press-fitted, a high-friction mounting process called chassis in French, directly onto the extended central arbor of the rotating kinematic component, which is usually a brass star wheel. Because the hand sits above the dial and must rotate freely over it, this design inherently requires vertical clearance in the z-axis. This means the watch case must have enough room between the dial surface and the sapphire crystal to accommodate stacked, overlapping hands without them ever colliding during operation. From a dial layout perspective, watchmakers generally utilize two distinct aesthetic approaches. The first is subsidiary dials, clearly seen on the Blancpain model on the left. In this layout, the date, day, and month each have their own dedicated, isolated microregisters. It is highly elegant, classical, and separates the data cleanly. The second approach is the central sweep, shown on the right. Here, an exceptionally long date hand pivots from the very center of the movement, sweeping across a 1:31 track printed on the extreme outer or inner perimeter of the dial. This maximizes legibility by utilizing the dial's absolute largest circumference. Both methods offer a deeply traditional aesthetic but require robust central pivoting mechanics. Now let's examine paradigm 2, the disc, or disc indication. This is arguably the most common, robust, and legible calendar display utilized in modern mass-produced wristwatches. Look at the exploded CAD diagram on the screen to understand its layers. In this architecture, the physical pointing hands are completely replaced by flat, rotating discs. For the date indication, we use a specialized component called the couronne, or date disc. This is a massive, flat, crown-shaped internal gear ring that spans the entire outer perimeter of the movement. It is manufactured to be ultra-lightweight, often cut and turned from thin brass, aluminum, or injection molded from synthetic materials specifically to minimize the torque required from the mainspring to turn it. The 31 numerals are transfer printed or decaled onto its upper face. Directly above this rotating disc sits the main dial plate. The genius of this design is the guichet, which is the precise rectangular aperture cut into the dial. The dial acts as a solid mask, hiding the complex mechanics and the other 30 numbers, exposing only the single relevant piece of data for that specific day. There is a crucial manufacturing constraint here that engineers must plan for: the sequence of the printed numbers on the ring, whether they read clockwise 1, 2, 3, or counterclockwise 31, 30, 29, is dictated entirely by the final rotation direction resulting from the specific underlying gear train architecture. The dial printer must absolutely know the kinematics of the movement before printing a single disc. In the realm of modern high horology, watchmakers are not strictly bound to use just one paradigm. This brings us to synthesis, mixed indication systems. Here, master watchmakers combine both hands and discs to optimize dial legibility while perfectly managing the internal mechanical layout. Look at the incredibly beautiful Blancpain calendar watch on the screen. It perfectly illustrates this hybrid approach. For the date indication, it utilizes a hand-based egg-wheel system. A gorgeous, blued steel central sweeping pointer with a crescent tip stretches all the way out to indicate the 1 through 31 numerical track on the extreme outer perimeter of the dial. However, for the day of the week and the month, it switches entirely to a disc-based disc system. You can clearly see two rectangular guichets situated just below the 12 o'clock position, revealing flat printed plates rotating silently beneath the dial. Finally, the moon phase is also disc-based, revealed through a specialized semicircular aperture known as a bosom window at the 6 o'clock position. Why go through the trouble of combining these systems? It is a masterclass in spatial ergonomics. Combining the paradigms allows the designer to present a massive amount of information, a full triple calendar with a moon phase, without cluttering the dial with too many overlapping hands. Simultaneously, it keeps the overall thickness of the movement profile as slim as possible, which is a hallmark of luxury dress watches. It is the perfect marriage of aesthetics and mechanical efficiency. Now we transition from the visual dial interface into the deep, hidden mechanics. How do we actually power these displays? Let me introduce you to the kinematics of the date gear train, known in Swiss terminology as the rouage de quantime. Look closely at the energy flow diagram on the screen. We start on the far left with the mainspring, the beating heart of the watch. It drives the going train, which in turn drives the motion work to turn the minute in our hands. The absolute critical reality you must understand right now is this: the calendar mechanism possesses no independent power source of its own. Every single microjoule of kinetic energy required to overcome the friction of stiff jumper springs and to advance heavy brass indicator discs is strictly parasitic. It is siphoned directly from the base timekeeping gear train. Specifically, the power is drawn from the hour wheel, or roue d'heures. But here we encounter our primary mechanical problem: the hour wheel rotates exactly 2 times per 24 hours. As we established earlier, the calendar indicator must advance exactly 1 time per 24 hours, striking right around midnight. Therefore, the calendar gear train must be engineered as a mandatory 1-to-2 reduction train, or rouage demultiplicative. It must mathematically have the rotational speed of the hour wheel. We will now look at the 2 distinct engineering methods used to achieve this vital step-down in speed. Let's examine method 1 for achieving this mandatory 1:2 speed reduction, the direct drive architecture. As the name implies, this system operates entirely without an intermediate wheel. Look at the mechanical schematic on the screen to trace the power flow. In this highly compact, robust layout, the hour wheel on the left meshes directly with the driving wheel of the 31-tooth date star on the right. This large driving wheel is equipped with an integral driving finger that physically pushes against the teeth of the 31-tooth star. Once pushed, the star is caught and held firmly in its resting position by a high-tension click spring, known as a sautoir. What is the engineering trade-off for choosing this specific architecture? The pro is undeniable: it is a highly compact system with a minimal part count, offering highly efficient energy transfer since there are no intermediary gears to cause parasitic friction loss. The con, however, is a severe limitation on design flexibility. Because there are no intermediate gears to bridge spatial gaps across the movement plate, the date indicator, whether a disc or a hand, must be positioned exactly adjacent to the hour wheel. This rigidly dictates where the date can visually appear on the dial, severely restricting the watch designer's aesthetic layout options. It is efficient, but structurally inflexible. To make method 1 function flawlessly, the watchmaker must obey a strict mathematical imperative. Let's look at the gear ratio formula displayed prominently on the screen. It is elegant and absolute: N2/N1 equals Z1/Z2, which must equal 1/2. Let's carefully define our variables so you understand the physics. Z1 represents the number of teeth on the hour wheel, our power source. Z2 is the number of teeth on the 31-star driving wheel. N1 represents the rotational speed of the hour wheel, which we know is exactly 2 revolutions per day. N2 is the target rotational speed of our driving wheel, which absolutely must be 1 revolution per day to change the date at midnight. Let's run a quick worked example. To have the rotational speed directly, the driven wheel must have exactly double the number of teeth of the driving wheel. If the base movement provides an hour wheel, Z1, manufactured with 24 teeth, then the calendar driving wheel, Z2, must be milled with exactly 48 teeth. 24/48 gives us our mandatory 1/2 reduction ratio. It is a simple, direct, and unyielding mechanical ratio that mathematically guarantees the date finger strikes the calendar star exactly once every 24 hours. Now let's look at method 2, the compound gearing architecture. Unlike the previous method, this system actively utilizes an intermediate wheel. Look at the complex, beautiful gear train layout on the screen. In this architecture, the hour wheel does not drive the date mechanism directly. Instead, it drives a compound intermediate mobile. This mobile consists of 2 toothed elements, a larger wheel and a smaller pinion, that are rigidly joined together, either by heavy press fitting or riveting, so they turn together on the exact same arbor. The hour wheel drives the intermediate wheel, and then the intermediate pinion meshes with and drives the final date indicator driving wheel. What is the immense engineering advantage of adding this extra gearing complexity? It completely divorces the physical location of the date indicator from the dead center of the movement. By using this compound gear train as a physical kinetic bridge, the watchmaker gains total freedom over the placement of the calendar complication within the caliber. This is the exact architecture that allows for those massive, ultra-legible outer ring date discs, the courants, which sit far away from the central hour wheel at the very edge of the dial. It deliberately trades mechanical simplicity for absolute architectural freedom. Because method 2 uses a compound gear train, the mathematics required to achieve our 1-to-2 reduction becomes slightly more involved. Let's examine the compound mathematical imperative. Look at the expanded formula: N4/N1 equals Z1 times Z3, divided by Z2 times Z4, which must still equal our golden target of 1/2. Let's break down these variables. Z1 is the hour wheel, our primary driver. Z2 is the intermediate wheel, the primary driven gear. Z3 is the intermediate pinion, acting as the secondary driver on that shared axis. And Z4 is the final date indicator driving wheel. N1 and N4 remain their respective rotational speeds. The mechanical principle here is that the strict 1:2 reduction is achieved not by a single gear pair, but by multiplying the ratios of the two sequential meshing gear pairs. For example, if Z1 is 24 teeth, Z2 is 48 teeth, Z3 is 8 teeth, and Z4 is 16 teeth. 24 times 8 is 192. 48 times 16 is 768. 192 divided by 768 perfectly equals 1/4. If the math doesn't hit exactly 1/2, the engineer simply recalculates and changes the tooth counts of Z2, Z3, and Z4 until the final product exactly halves the input speed. This compound formula is the absolute bedrock of modular calendar design. Regardless of whether the engineer chooses method 1 or method 2 to reduce the speed, the kinetic energy eventually reaches the ultimate component, the actuation architecture, specifically the date driving wheel, or roue entraîneurs. Look at the pristine brass component rendered on the screen. This wheel is the primary interface between the continuous, flowing time of the base movement and the discrete, snapping jump of the calendar. The component consists of a base wheel plate, known as the planche de roue. This plate receives the continuous, slow, step-down rotary motion from our 1:2 reduction gear train, spinning exactly once a day. Mounted firmly on top of this plate is the critical actuating element, the driving finger, or doigt d'entraînement. This finger acts exactly like a single, highly specialized gear tooth. Its primary, vital function is to translate continuous rotary motion into a daily, single-step, discrete actuation. Once every 24 hours, this finger swings around, makes physical contact with the teeth of the date indicator, forcefully pushes it forward by exactly one position, and then continues its rotation, leaving the indicator completely alone until the next midnight. It is a masterpiece of intermittent kinetic motion. Not all driving fingers are created equal. Let's examine the actuation architecture, driving finger typologies. Depending on the manufacturing budget, durability requirements, and caliber grade, Swiss watchmakers rely on 3 primary types of driving fingers. Type 1 is the pressed pin, or goupil chassis. This is a very simple cylindrical steel pin friction-fitted tightly into a precisely drilled hole in the brass wheel plate. It is highly reliable, incredibly strong, and very cost-effective to manufacture in high volumes. Type 2 is the bent tab, or ergot. This finger is formed integrally by cutting a specific shape directly into the wheel plate and bending it upward at a strict 90-degree angle. This is highly efficient for mass production as it entirely eliminates the need for a second component. Type 3 is the riveted piece, or piece rivet. Here, a separate, precisely machined brass or steel finger is pressed or riveted onto the wheel's central hub, or cannon. This is used extensively in higher-end calibers because the finger's contact geometry can be machined to extreme, microscopic precision. Crucially, in high-end horology, these fingers are often engineered to be retractable or escamotable. This is a vital safety mechanism. If a user incorrectly sets the watch near midnight while the finger is engaged, a retractable finger will yield and fold backward, preventing catastrophic mechanism damage. We will cover these safety systems in depth in Part 2. Once the driving finger finally strikes, what exactly is it hitting? Let's dissect the indicator anatomy, the date disc, known traditionally as the couronne. Look at the detailed 3D rendering on the screen. Structurally, the couronne is a large, flat annular ring. It is meticulously manufactured from cut and turned brass or aluminum, though modern mass-produced movements frequently use molded synthetic materials like Delrin. The engineering goal here is to drastically minimize mass and rotational inertia to reduce the parasitic torque drain on the delicate mainspring. The upper face is the visual component you see through the dial. It is transfer printed or decaled with the 31 numerals. The rotation direction, whether it turns clockwise or counterclockwise, strictly dictates whether the numbers are printed sequentially or in reverse. The inner face is the hidden mechanical component. It is precisely machined with exactly 31 internal teeth. These internal teeth serve a brilliant dual kinematic purpose. First, actuation, they provide the flat vertical surface to receive the direct horizontal thrust force from the driving finger to advance the disc. Second, stabilization. They provide the exact geometric values where the jumper spring engages, securely locking the ring to ensure the date numeral aligns perfectly within the dial window. If the watch uses a physical sweeping hand instead of a rotating disc, the internal anatomy of the indicator changes completely. Let's look at the indicator anatomy for the egg wheel paradigm, the date star, or étoile de 31. Look at the star wheel diagram on the screen. Application-wise, this specific date star architecture is used exclusively when the calendar information is indicated by a physical hand pointing to a subdial or outer track. Structurally, it is a small, centrally or eccentrically located brass gear containing exactly 31 teeth. The indicating hand is friction-fitted directly onto the star's central extending arbor, protruding through the dial. The absolute most critical engineering feature here is the tooth geometry. Unlike the standard involute gears you find in the going train, which are designed for continuous, smooth rolling mesh, the teeth of a date star are sharply pointed. Why? Because this acute, triangular geometry ensures that when the jumper spring presses down heavily between them, it exerts a massive, immediate self-centering force. It violently snaps the star perfectly into its resting position, ensuring the date hand points exactly at the numeral on the dial, with absolutely no visual slop or mechanical play. I have mentioned the jumper spring several times today. Let's finally examine it in detail. This is the crucial mechanism of stabilization and alignment, the jumper spring, or sautoir. Look at the dynamic tension diagram on the screen to understand how it interacts with the gear teeth. The primary, indispensable function of the sautoir is to secure the resting position of the calendar indicator. Whether it's locking a 31-tooth star or a massive date disc, the jumper spring prevents any drift or misalignment caused by physical shocks, violent vibrations from the wearer's wrist, or simple gravity. Mechanically, it is a precisely shaped steel spring featuring a highly polished, V-shaped geometric head. This head is under constant, heavy spring tension, forcing it to lodge firmly into the deep valley between two teeth of the indicator. Its kinematic roll provides that highly satisfying mechanical click you feel and hear at midnight. It guarantees crisp, exact alignment of the date within the dial window. When the driving finger pushes a tooth past the very apex of the jumper head, the jumper's stored compressive tension suddenly releases. It forcefully snaps the mechanism forward into the next day, locking it rigidly in place. Without the sautoir, the date would float loosely and look broken. This brings us to the conclusion of part 1. Let's synthesize everything we've learned today into our horological baseline before we tackle the more advanced kinematics tomorrow. We began by tracing the deep history of calendar watches, from massive 16th century astronomical clocks to Breguet's legendary 1827 Marie Antoinette pocket watch, evolving finally into shockproof 20th century wristwatches. We established the official terminology 1, 2, and 3 quantime indicating the sheer volume of data displayed on the dial. We explored the two fundamental display paradigms, the physical sweeping hands of the egg wheel system and the rotating, hidden discs of the disc system, which can be elegantly combined for optimal dial legibility. Crucially, we dissected the kinematic imperative, the absolute, mathematical requirement for a 1:2 gear reduction train, stripping parasitic power from the 12-hour wheel to provide a single, once-a-day rotation for the driving wheel. We saw how this driving wheel uses a specialized finger to actuate the 31-tooth date star or couronne, which is finally locked into perfect visual alignment by the high-tension jumper spring. You now understand the fundamental physics of the basic calendar drive. But how does the date actually change at midnight? Is it a slow crawl? Is it a violent snap? Is it dangerous to set the time? In part 2, we will dive into the 3 specific mechanisms of the date changeover, the trailing, the semi-instantaneous, and the instantaneous architectures. Thank you for your exceptional attention today, and I will see you in the next module. Welcome back, everyone, to part 2 of our comprehensive deep dive into Chapter 9, Calendar Mechanisms. Please take your seats. In our first session, we laid the absolute groundwork. We established the historical evolution of the calendar watch, examined the fundamental display paradigms, hands versus discs, and, most importantly, we mathematically decoded the 1:2 gear reduction ratio. We now know exactly how to step down the rapid rotation of the hour wheel to provide a single, daily kinetic impulse. But knowing how to deliver that impulse is only half the battle. The true artistry of horological engineering lies in when and how fast that date change occurs. Today, we are going to deconstruct the exact kinematics of the date changeover. We will look at the three distinct mechanical approaches developed by watchmakers over the centuries: the leisurely trailing mechanism, the crisp semi-instantaneous mechanism, and the highly complex instantaneous mechanism. Beyond just the automatic midnight change, we must also confront the human element. How does a user manually correct the date for a short month without completely destroying the delicate micromechanics inside? We will explore the mechanical interfaces of manual correction, both case pushers and winding crowns, and we will meticulously analyze the autonomous safety failsafes, like the spring-loaded finger, engineered specifically to prevent user-induced catastrophic failures. This module is all about the physics of the midnight transition and protecting the machine from its owner. Let's dive in. To understand how a date changes, we must look at the comparative architecture of the three fundamental approaches. Please direct your attention to the matrix on the screen. The evolution of date mechanisms directly reflects a centuries-long horological drive for clearer, more precise, and more legible displays. In the first column, we have the trailing mechanism, or mechanism trainant. Notice the primary characteristic: it completely lacks a jumper spring. The transition duration is an agonizingly slow 2 hours, and it stores absolutely zero kinetic energy. The positioning relies entirely on the constant, dragging friction of the driving wheel. It is the oldest and simplest method. In the middle, we have the modern standard, the semi-instantaneous mechanism. Here, we introduce the jumper spring, or sautoir. The transition duration shrinks to approximately 90 minutes. It stores moderate potential energy by slowly compressing the jumper spring, resulting in a crisp, rapid snap into the next day. The positioning is dictated purely by the jumper spring locking the gear teeth. Finally, on the right, we reach the pinnacle, the instantaneous mechanism. Like the semi-instantaneous, it utilizes a jumper spring, but the transition is near instant, taking less than a single second at exactly midnight. To achieve this violent burst of speed without stalling the watch, it requires massive energy storage, preloading a dedicated heavy-duty spring over several hours. The evolution here is clear. Watchmakers continuously fought to decouple the slow accumulation of energy from the visual actuation of the indicator. Let's begin our deep dive with the oldest and simplest architecture, the trailing mechanism, or mechanism trainant. Look closely at the incredibly complex gear train schematic on the screen. The core defining principle of this entire system, the red warning box you must remember, is that there is absolutely no jumper spring. The driving wheel acts as the sole positioning agent for the date indicator. Let's trace the kinematic pathway. Power flows from the hour wheel, 1, through an intermediate mobile, 2, and into the 24-hour wheel, 3. This 24-hour wheel carries a specialized driving finger, 4. Once a day, this finger engages and drives a beautifully machined Maltese cross, or croix de Maltais, 5. This Maltese cross is engineered to rotate exactly 90 degrees, 1/4 turn per day. Rigidly fixed to the bottom of this Maltese cross is a tiny 8-tooth pinion, 6. This pinion is permanently, constantly meshed with the massive date indicator ring, 7. Here is the mathematical insight you need: the date indicator possesses exactly 62 internal teeth. Since the 8-tooth pinion turns 1/4 of a revolution, it advances exactly 2 teeth. 2 teeth per day multiplied by 31 days equals exactly 62 teeth. The math is absolute perfection. Now, let's put this machine into motion and observe the step-by-step kinematics of the trailing mechanism. Follow the timeline at the bottom of the screen, starting at 2300 hours and stretching all the way past 1 o'clock. This is not a fast process. At step 1 and 2, the base drive is simply turning the 24-hour wheel. It takes a full 24 hours for the finger to complete its lazy orbit. At step 3, as we approach midnight, the engagement begins. The 24-hour wheel finger slowly enters the open slot of the Maltese cross. Moving into step 4, the actuation occurs. The continuous rotation of the 24-hour wheel forces the Maltese cross to slowly turn exactly 1/4 of a revolution, or 90 degrees. Consequently, in step 5, the rigidly attached 8-tooth pinion also rotates 1/4 turn, which equates to an advance of exactly 2 gear teeth. Finally, in step 6, this slow, deliberate rotation is transmitted to the 62-tooth indicator, advancing it by 2 teeth, representing 1 calendar day. The kinematic reality here is crucial, because there is no click spring to snap it forward. The mechanism simultaneously pushes and pulls it train, or drags, the date indicator across a leisurely, agonizingly slow 2-hour window. The date physically crawls through the dial aperture. If you were paying close attention to the architecture of the trailing mechanism, you should have noticed a massive mechanical paradox. The 8-tooth pinion is permanently and rigidly meshed with the 62-tooth date indicator. So, at the end of a 30-day month, how on earth does the user manually advance the date to the first without physically shattering the gear train? The mechanical solution is brilliantly simple and relies entirely on z-axis vertical displacement. Watchmakers utilize a specialized milled recess in the brass mainplate, called a noyeur. Look at the cross-sectional CAD profile on the screen. In the normal state on the left, the Maltese cross and its pinions sit flat, perfectly engaged with the date indicator. But look at the correction state on the right. When the user actuates the manual date corrector, the external force physically pushes against the date indicator. Because the teeth are angled, this lateral force causes the entire Maltese cross and pinion assembly to deflect and physically shift laterally and slightly upward, sliding backward into that milled recess, the noyeur. It completely drops out of engagement. The date indicator is now free to spin. The exact moment the user finishes the correction, a dedicated heavy return spring, the ressort de rappel, violently snaps the pinion assembly back out of the recess, forcefully restoring perfect engagement. Let's synthesize our understanding of the trailing mechanism by evaluating its engineering characteristics and why it eventually fell out of favor. Look at the diagnostic matrix on the screen. On the left, we have the engineering advantages. It boasts an incredibly simple construction with a very low component complexity. Because the gears roll continuously rather than snapping violently, it offers a beautifully smooth, continuous wear profile on the teeth, extending the lifespan of the brass. Furthermore, the complete absence of a high-tension jumper spring means there is very little parasitic torque drain on the mainspring. However, look at the inherent flaws on the right. The first is an ambiguous readout. Because it takes 2 hours to drag the date wheel, there is a massive transitional window from roughly 11 p.m. to 1 a.m. where the date is visually misaligned in the dial aperture. You might see half of the 14 and half of the 15, making it impossible to read at a glance. The second, fatal flaw is shock vulnerability. Without a jumper spring, the date is never physically locked in place. A hard knot to the watch case can easily shift the untensioned indicator out of alignment. Because of these flaws, this system was historically dominant only in early pocket watches, where the watch sat safely and statically in a waistcoat pocket. Recognizing the fatal flaws of the dragging mechanism, the Swiss watchmaking industry evolved. Enter the semi-instantaneous mechanism, or mechanism semi-instantane. This is the undisputed modern standard. It is, without question, the most widely used calendar architecture in contemporary wristwatch horology. Look at the gorgeous CAD rendering on the screen. The defining element, the game changer, is highlighted in red, the jumper spring, or sautoir. This heavy, precisely shaped steel spring lodges deeply and aggressively between the indicator teeth. Its sole purpose is to securely and unyieldingly lock the date wheel in its resting position, making it entirely immune to shock. Providing the immense pressure for this jumper is a tensioner, typically a flat or wire spring maintaining continuous high-pressure compressive force. Below that, we have the driving finger. It is a standard, continuous rotation finger rigidly mounted to the 24-hour wheel. But here is the massive kinematic shift you must comprehend. Unlike the trailing system we just studied, the driving wheel here does not determine the final position of the indicator. It merely provides the raw pushing force to overcome the jumper spring. The sautoir, and the sautoir alone, dictates the final, mathematically precise locked position of the date numeral within the dial aperture. Let's break down the exact physics of how this mechanism creates that highly satisfying click at midnight. We are looking at the physics of the snap in 4 distinct phases. Phase 1 is initiation. At approximately 22:30, the continuous rotation of the 24-hour wheel brings the driving finger into physical contact with the flat edge of a date tooth. The push phase begins. Phase 2 is the load phase. Over the next 90 minutes, the driving finger relentlessly pushes the tooth forward. Because the date wheel is being forced to rotate, the acute geometry of the tooth is forced to lift that heavy, high-tension jumper spring. Potential energy begins to heavily accumulate in the spring. Phase 3 is the absolute critical apex, known in French horology as sommet sur sommet, or tip-to-tip. At exactly a fraction of a second before midnight, the polished tip of the jumper spring perfectly aligns with the absolute microscopic apex of the star tooth. For one singular millisecond, the pushing force of the finger and the downward force of the spring achieve exact, terrifying equilibrium. Phase 4 is the snap. The driving finger pushes just 1 micron further. The equilibrium shatters. The jumper spring slides past the apex, and its massively stored kinetic force violently overcomes the driving finger. The spring rapidly and aggressively snaps the indicator forward, plummeting down the back slope of the tooth to lock it securely into the next valley. The date has changed. To truly grasp the reality of the semi-instantaneous system, we must visualize the timing of these events. I want you to look at the engagement zone timeline on the screen, stretching from 2100 hours on the left to 1 o'clock on the right. Prior to 2230, the mechanism is in pre-engagement. The driving finger is merely sweeping through empty space, doing absolutely nothing to the date wheel. But at exactly 2230, initial contact occurs. The mechanism is now actively meshed. This begins the red engagement zone. From 2230 all the way to 2355, the mechanism is under immense and building pressure. This 90-minute window is purely mechanical preparation. The date numeral in the window might creep slightly upward, but the shift hasn't happened. At exactly 2355, we hit maximum tension, the tip-to-tip state. Component stress is at its absolute highest peak. Then, right at midnight, the snap occurs. This is the visual change, and it happens in a matter of milliseconds. The user perceives the change as instantaneous. Finally, by 0:30, disengagement is complete. The driving finger has fully cleared the path of the star wheel teeth. The key insight here is profound. While the visual date shift is near instantaneous, the mechanical reality is a grueling 90-minute marathon of friction and spring compression. Let's evaluate the semi-instantaneous mechanism. Why did it become the global standard, and what are its hidden dangers? Let's look at the synthesis matrix. The engineering advantages are clear. First, it provides crisp, definitive readability. The user wakes up, looks at their watch, and the date is perfectly centered. Second, positive locking. Because the sautoir applies constant, heavy pressure, the date disc is completely immune to shock-induced drift. You can play tennis or golf, and the date will not shift. Third, it offers massive modular versatility. It is easily bolted onto standard gear trains without redesigning the base caliber. But look at the mechanical vulnerabilities on the right. The very spring that secures the date also introduces severe friction wear. The jumper spring adds a permanent, high-pressure sliding wear surface that requires highly precise, specialized heavy lubrication to prevent the brass teeth from grinding away. You also experience visual creep, where the date numeral visibly shifts slightly out of center starting around 2230 as the tooth climbs the spring. But the most critical vulnerability is the danger zone. Because the driving finger is physically interwoven and meshed with the date wheel from 2200 hours until 0:30, it creates a rigid mechanical bind. If a user attempts to manually quickset the date during this 2.5-hour window, they will force the gears to collide, resulting in catastrophic damage. This is the Achilles heel of the semi-instantaneous design. For the highest echelon of luxury watchmaking, the 90-minute visual creep and the heavy friction of the semi-instantaneous system were deemed unacceptable. Thus, engineers developed the instantaneous mechanism, or mechanism instantane. Let's explore its governing philosophy. Look at the graph on the screen comparing stored energy against time. The ultimate goal of this mechanism is to produce a massive, lightning-fast date jump at exactly midnight, with absolutely zero visual pre-travel. The date must remain perfectly dead-centered until the exact millisecond of midnight. However, the engineering challenge is immense. If you try to draw the massive amount of torque required to snap a heavy date disc instantly from the going train at midnight, the sudden, violent power drain will literally stall the balance wheel. It will ruin the watch's chronometry, causing it to lose seconds or stop entirely. The genius decoupling solution, known as armage or charging, is visualized by the blue ramp on the graph. Instead of drawing power at midnight, the mechanism slowly siphons microscopic amounts of energy from the base movement over a massive 7-hour charging phase, beginning around 1700 hours. It isolates and stores this energy in a dedicated, heavy-duty return spring. Then, at exactly midnight, it dumps all that stored energy instantly, driving the date wheel completely independently of the going train. It is a mechanical capacitor. How do we build a mechanical capacitor? Let's examine the instantaneous architecture, specifically the bascule system. Look at the intricate CAD blueprint on the screen to identify the components that make the 7-hour decoupling possible. The absolute heart of this system is the key component, the date-driving rocker, or bascule entreneurs de quantum. This is a massive, multi-arm lever that pivots within a dedicated recess in the main plate. Component 1 is the 24-hour wheel finger. Notice carefully, this finger does not touch the date indicator. It only touches and lifts the rocker arm. Component 2 is the tension spring, a light spring whose only job is to keep the rocker pressed tightly against the 24-hour finger so it tracks smoothly. Component 3 is the true powerhouse, the capacitor, or return spring. This is a massive, heavy-duty spring that stores the accumulated mechanical energy as the rocker is slowly lifted over 7 hours. Finally, component 4 is the actuation pin, mounted on the far end of the rocker. It is positioned with microscopic clearance so that it strikes the date indicator only upon the violent release of the rocker, not during the lifting phase. It is a masterpiece of delayed kinetic delivery. Let's put the bascule system into motion and trace the instantaneous kinematics through its 4-phase cycle. Watch how the energy builds and releases across the 4 panels on the screen. Phase 1 begins around 17:15. This is when the arming begins. The 24-hour wheel finger makes its initial contact with the rocker arm. The massive return spring just begins to flex. Crucially, the date indicator remains completely untouched and perfectly centered by its jumper spring. Phase 2 occurs around 2000 hours. Energy accumulation is well underway. The rocker has been lifted significantly by the slow rotation of the 24-hour wheel. There is now a high load of potential energy stored in the return spring. The actuation pin is hovering, resting gently, but applying no forward force. Phase 3 hits exactly at 23:55. This is maximum tension. The tip of the rocker sits at the absolute, precarious apex of the 24-hour finger. The return spring is screaming with stored potential energy. The entire system is cocked and ready like a loaded firearm. Phase 4 happens at exactly 0:05. The instant release. The continuous rotation of the 24-hour will causes the finger to slip past the rocker tip. With nothing holding it back, the massive return spring violently fires the rocker back to its resting position. As it snaps down, the actuation pin brutally strikes the date indicator tooth, advancing the heavy disc instantly in a matter of milliseconds. The stored energy does all the work, leaving the balance wheel's amplitude completely unaffected. We have successfully engineered the automatic midnight changeover. But watches exist in the real world. Months have 28, 29, or 30 days, and mechanical watches eventually run out of power and stop. Therefore, we must allow the user to intervene. Let's look at manual intervention method A, corrector pushers, or remise. Look at the cross-sectional diagram on the screen. The purpose of this system is to provide an essential, robust interface for the user to manually advance the calendar indications when the 31-day mechanical cycle falls out of sync with the actual Gregorian calendar. Let's examine the architecture and dynamics. These correctors are actuated via a pointed tool like a wooden stylus or a specialized pin pressed directly into a recessed pusher located on the case middle, or carrure. The mechanical logic is strictly binary, one press equals one discrete mechanical step. When pushed, the internal cylinder slides forward, physically engaging and advancing the star wheel exactly one tooth. Crucially, an independent return spring forcefully restores the pusher to its flush, resting position the instant the user releases pressure. The final positioning of the indicator remains autonomously governed by the internal jumper spring, ensuring perfect dial alignment. This method is the absolute standard in highly complicated calendars, like perpetual or annual calendars, where multiple independent indications such as the day, month, and moon phase require separate, isolated setting points without cluttering the winding crown. While case pushers are excellent for high complications, modern consumers demand convenience. This brings us to manual intervention method B, the winding crown. This is the rapid set date system you likely use on your own mechanical watches. Look at the kinematic routing on the screen. This system utilizes a 3-position architecture for the winding stem, or tige. Position 1, pushed fully in, is for winding the mainspring. Position 2, pulled out one click, is the rapid date setting, or mi-solid date repeat. Position 3, pulled fully out, hacks the movement to set the time. Let's trace the position 2 kinematics. When the user pulls the stem to position 2 and turns it, the stem engages the first return wheel, the renvoi. Power flows smoothly to a second return wheel. This second wheel drives a third return wheel which carries the magical component, the 3-arm cam, or CAMA 3 bras. This cam sits adjacent to the date disc. For every 120 degrees of rotation of this cam, one of its 3 arms physically engages a tooth and advances the indicator exactly 1 step. One full rotation of the crown yields multiple days of rapid advance. But heed the hazard warning at the bottom: never attempt to advance the calendar by manually winding the hands through 24-hour cycles in position 3. While it works, doing this repeatedly causes catastrophic, premature wear to the cannon pinion friction fit, the lanternage de la chaussée, which will eventually prevent the hands from turning at all. Always use position 2. I have mentioned the phrase catastrophic damage several times. Now, we must confront exactly why that happens. Welcome to the danger zone, the physics of catastrophic interference. This is the most critical operational warning in all of calendar horology. Look at the red warning graphic on the screen. The rule is absolute: do not correct the date manually between approximately 2200 hours and 0:30. Let's examine the physics of interference to understand why. Look at the safe state diagram on the top right. During normal daytime operation, there is massive clearance between the automatic driving finger and the teeth of the date disc. Using the rapid set crown to spin the disc is perfectly safe. But look at the crash state diagram below it. From 22 to 0:30, the automatic driving finger has physically swept into the path of the date disc and is actively meshing with a tooth to perform the midnight change. If the user pulls the crown and forces a manual quickset during this window, they are violently forcing the disc teeth directly against a rigidly locked, unyielding automatic finger. The modes of catastrophic failure are terrifying. The immense torque from the user's hand will result in shearing or snapping the steel driving finger entirely off its plate. It can strip the brass teeth right off the date star. Or, the sudden violent jump can shatter the highly tempered, brittle jumper spring. You are pitting the brute force of a human hand against microscopic brass and steel. The hand always wins, and the watch always dies. Because humans are inherently forgetful and will inevitably try to set their watches at 11:30 p.m., watchmakers had to engineer solutions to protect the machine from its owner. Let's examine failsafe architecture 1, the spring finger, or Deuteresort. The core concept here is brilliant: create a flexible joint designed to autonomously yield to user error, while still acting as a perfectly rigid pusher during normal, slow automatic operation. Look at scenario 1 on the left, the midnight quickset. It is 11:30 p.m. The driving finger is deeply engaged with the star wheel. The user foolishly forces the date wheel using the crown. The star tooth violently strikes the static finger. Instead of snapping, the finger yields. It folds sideways on a pivot against the pressure of a tiny internal spring, allowing the star tooth to pass harmlessly by, preventing breakage. Look at scenario 2 on the right, reverse time setting. The user pulls the crown to position 3 and winds the hands backward past midnight. The hour wheel reverses, forcing the driving wheel to turn backward. The back, or base, of the driving finger slams into the flat back of the star tooth. Once again, the finger yields backwards, folding in on itself to prevent jamming the gear train. The result? Once the mechanical hazard has cleared, once the tooth has passed, the internal spring tension automatically snaps the finger back to its rigid vertical posture, ready to resume normal operation. It is an elegant, autonomous defense mechanism. While the spring finger is excellent for mass-market calibers, high-end Haute Horlogerie demands an even more robust, friction-free solution. Let's examine failsafe architecture 2, the free-rotating finger system. This is a masterclass in 3D spatial engineering. Look at the exploded isometric diagram. Instead of a folding finger, this system uses a free pivoting finger that floats entirely unattached on the central hub. It is driven forward only by a separate fixed pin pressed into the wheel below it. Holding the finger down in its working plane is a heavy vertical spring bridge, or Pentresort. Let's look at how it defends against the midnight quickset hazard via lateral pivot. If the user forces the indicator at midnight, the indicator tooth violently pushes the finger away from the fixed driving pin. Because it is free floating on the hub, the finger simply pivots harmlessly out of the way. The driving wheel remains perfectly static, and no gears clash. Now, let's look at the reverse time setting defense via vertical deflection. If the user wins the hands backward, the driving wheel turns in reverse. The fixed pin comes up behind the free finger and strikes an inclined ramp machined into the back of the finger. Instead of jamming, the pin acts like a wedge. It forces the entire finger to deflect vertically. It literally lifts up in the Z-axis, sliding safely underneath the pin. Once the pin passes, the massive spring bridge forcefully presses the finger back down into flat engagement. It is true, three-dimensional mechanical protection. To truly appreciate these failsafes, we must compare them side by side. Let's look at the safety diagnostics mechanism assessment matrix to understand why a watchmaker chooses one over the other. First, let's look at hazard protection. Both the spring finger and the free rotating finger successfully protect against both major hazards, the midnight quickset clash and the reverse time setting jam. They both achieve the primary goal of saving the movement. However, look at the yield vector. This is how they actually move to escape the crash. The spring finger relies purely on horizontal deflection. It folds sideways within the 2D plane of the gear train. The free rotating finger is vastly superior here. It utilizes a lateral pivot for one hazard, and a vertical Z-axis deflection into 3D space for the other, ensuring absolute clearance. Component complexity dictates their usage. The spring finger is relatively low complexity. It is essentially one highly complex, integrated part comprising a hub, a hinge, and a micro spring. The free rotating finger is moderate complexity, requiring at least three distinct, robust parts: the pin, the finger, and the heavy spring bridge overhead. Consequently, their application tiers differ. Because it is easier to assemble, the spring finger dominates mid-range and mass-market calibers where automated assembly is required. The free rotating finger, requiring meticulous manual adjustment of the spring bridge tension, is reserved almost exclusively for high-end and Haute Horlogerie calibers, where durability and longevity trump assembly cost. We have reached the end of Part 2. Let's bring everything together in our Part 2 synthesis, the horological baseline. We have covered a tremendous amount of mechanical theory today. We deconstructed the three kinematics of date changeover. We saw the 2-hour drag of the trailing mechanism and its clever recess clutch. We analyzed the modern standard, the semi-instantaneous, which preloads for 90 minutes before a millisecond snap, unfortunately creating the infamous danger zone. And we marveled at the instantaneous mechanism, which decouples the timekeeping from the calendar entirely, storing energy over 7 hours for a massive, isolated strike at exactly midnight. We explored the user interface. We looked at case middle pushers, or remises, which offer independent, discrete steps for complex calendars. And we dissected the 3-position crown, utilizing a 3-arm cam for rapid, satisfying daily advances. Finally, we studied the failsafe architectures. We understand that humans make mistakes, and without protection, setting a watch at midnight will cause catastrophic structural failure. We reviewed how retractable spring fingers and free-rotating 3D yielding fingers autonomously sacrifice their positioning to absorb mechanical landmines, ensuring the structural integrity of the gear train survives for generations. You now possess a complete understanding of how a date wheel moves, snaps, and survives. But a date is just a number. In our next module, Part 3, we will apply these exact same physical rules to the day of the week, the month, and the incredibly poetic star wheel moon phase indications. Thank you for your attention, and I will see you in Part 3. Welcome back, everyone, and please take your seats as we begin Part 3 of our comprehensive journey into calendar mechanisms. In Parts 1 and 2, we established the fundamental rules of the calendar watch. We dissected the 1-to-2 gear ratio required to step down the 12-hour wheel, and we spent a great deal of time analyzing the exact kinematics of the midnight date changeover. We looked at trailing, semi-instantaneous, and instantaneous snaps, and we explored the ingenious failsafe devices engineered to protect these delicate components from user error. Now, we are going to expand our horological canvas. A calendar is much more than just a date from 1 to 31. Today, we are going to apply the exact same mechanical principles we've learned to track completely different scales of time. We will deconstruct the day of the week mechanism, the month indication, and we will finally bridge the gap between watchmaking and astronomy by introducing the star wheel moon phase. As we look at the dial schematic on the screen, I want you to appreciate the modularity of Swiss watchmaking. The brilliant engineers who designed these systems realized they didn't need to invent entirely new physics for each display. Instead, they took the proven architecture of the 31-tooth date mechanism and simply swapped out the star wheels to reflect different mathematical cycles. We are moving from a 31-step cycle to a 7-step cycle, a 12-step cycle, and finally, a 59-step cycle. Let's begin by examining how the watch tracks the days of the week. Let's start our examination with the day of the week mechanism. Please look at the architectural comparison on the screen, placing the 31-tooth date system right next to the 7-tooth day system. The most important concept to grasp here is the shared principle. The operating principle of the day indicator is absolutely identical to the date mechanism. Both are actuated once every 24 hours, striking simultaneously right around midnight. They share the exact same kinetic drive path. Power flows from the hour wheel to the 24-hour driving wheel through an integrated finger, which strikes a star wheel, which is finally locked into place by a high-tension jumper spring. However, the key difference is obvious in the geometry. The massive 31-tooth star is completely replaced by a much smaller, aggressive 7-tooth star, or étoile de 7. Mathematically, one tooth equals exactly one day of the week. This structural similarity provides a massive insight into modern manufacturing. It allows for highly streamlined, cost-effective production. In many modular calibers, the date and day gear trains are practically identical subassemblies. The manufacturer uses the exact same wheels, the same arbors, and the same jumper spring designs, differing only in the physical size and tooth count of the final star wheel. It is a masterpiece of mechanical economy. Let's break down the day of the week gear train into its specific component detail. Look at the exploded 3D rendering to trace the transfer of energy. Component 1 is the hour wheel, spinning twice a day. It meshes with Component 2, the day driving wheel, or roue entraîneuse de l'étoile de 7. Our kinematic output box confirms the math. Using the gear ratio formula N2/N1 equals Z1/Z2, we achieve our mandatory 1/2 reduction, meaning this driving wheel rotates exactly once per 24 hours. Integral to this driving wheel is Component 3, the driving finger. Once a day, this finger violently strikes Component 4, the 7-tooth star wheel, which serves as the day indicator driver. Finally, Component 5, the jumper spring or sautoir, slams into the valley between the teeth to lock the star. But I want you to read the critical engineering note at the bottom of the screen. Look at the immense gap between the teeth of the 7-tooth star compared to a 31-tooth star. A 31-tooth star requires a tiny jump of about 11.6 degrees. But a 7-tooth star demands a massive step angle of 51.4 degrees. 360 divided by 7. Because the jump is so incredibly wide, the jumper spring must span a much greater arc. Consequently, it requires significantly higher spring tension to securely snap the wheel across that massive void without bouncing. The day jump is inherently more violent than the date jump. Once the 7-tooth star snaps into place, how does the user read it? Let's look at the day indicator, disc type, or disc. This is the standard interface for modern sports and casual watches. Looking at the material specs, this flat plate is typically manufactured from cut and turned brass, lightweight aluminum, or, in high-volume production, precision-molded synthetic plastics. The goal is to keep the rotational mass as low as possible. On the upper face, the days of the week are transfer printed or decaled, usually using standard multilingual 3-letter abbreviations like MON, TUE, WED, or the French LUN, MAR, in the are seen here. Look closely at the structural load note on the right. Notice that the disc plate itself has absolutely no gear teeth on its perimeter. It is completely smooth. The brass 7-tooth star, which is permanently riveted to the bottom of the disc, provides 100% of the mechanical function. The star bears the structural load, receives the violent thrust from the driving finger, and absorbs the heavy impact of the jumper spring. The printed disc is merely a passive cosmetic billboard being dragged along for the ride. This modularity allows watch brands to instantly swap out English, French, or Japanese day discs on the assembly line without ever touching or modifying the underlying mechanical module. If the watch designer desires a more classical, vintage aesthetic, they will abandon the disc entirely and utilize the day indicator, hand type, or needle type. Look at the cross-sectional diagram comparing the two. In terms of structural integration, a delicate needle, the egg wheel, is friction-fitted, or press-fitted, directly onto the vertically extended arbor of the 7-tooth star wheel. Just like the disc version, the star's pointed teeth carry all the mechanical burden of actuation and locking. The needle simply points to a printed subsidiary dial, usually located at the 3 or 9 o'clock position on the main dial face. This architecture offers excellent mechanical economy. It features far fewer bulky components and a much simpler overall construction than the wide, overlapping disc types. However, it requires a very specific adjustment mechanics protocol during assembly. Because there is no printed disc that is permanently riveted in a fixed alignment, the watchmaker must manually achieve day alignment. They do this by physically rotating and pressing the needle's position on the arbor until it perfectly bisects the printed letters on the dial while the jumper spring is locked dead center in a gear valley. It requires a highly skilled, steady hand to calibrate. When you combine both the 31-tooth date disc and the 7-tooth date disc into a single movement, you create one of the most famous and practical mechanisms in horology, the date complication. Look at the incredibly dense, overlapping layout on the screen. The primary goal is simultaneous indication. It provides the wearer with both the date, the quantime, and the day of the week via two distinct, overlapping planar discs. You are likely familiar with this layout from the iconic Rolex Day-Date, which normalized reading the day fully spelled out at the 12 o'clock position, and the date at 3 o'clock. The engineering brilliance here relies on a shared power flow. Both of these completely independent mechanisms are driven seamlessly by the exact same 24-hour reduction train. The kinetic output is split. The single 24-hour will simply carries two separate driving fingers, or a single complex finger, designed to strike both the 31-tooth star and the 7-tooth star at precisely the same moment around midnight. However, this creates severe layout constraints. The movement designer must meticulously engineer the planar layout to accommodate these massive, overlapping discs. The date ring must be wide enough to clear the movement, while the day disc must sit slightly above or below it. It is a constant battle to fit these intersecting circles without adding excessive z-axis thickness to the watch caliber, which would ruin the elegant profile of the case. We have mastered the daily cycles. Now, we must dramatically scale up our temporal tracking. Let's examine the month indication, operating principle. We are moving from a cycle that updates every 24 hours to one that updates only once every 30 or 31 days. Look at the graphic on the screen. The heart of this system is the 12-tooth month star, or étoile de 12. Unlike the day and date indicators that are struck violently every single midnight, this month star sits perfectly dormant for almost the entire month. It is actuated and advances exactly one tooth, which is 1/12th of a full revolution, only at the very end of each month. The math is beautifully simple: 12 months multiplied by a one-tooth advance equals exactly 12 teeth. The result is that this star will complete exactly one full 360-degree revolution per calendar year. But here is the profound mechanical challenge: how does the watch know when the month has ended? The timekeeping gear train only knows hours and minutes. It has no concept of a month. Therefore, we cannot drive the month star directly from the 24-hour wheel. We must build a secondary event trigger mechanism that only fires after the date will has completed a full 31-day cycle. Let's see how watchmakers solved this hierarchical routing problem. To trigger an event only once a month, watchmakers developed the month indication gear train architecture utilizing a brilliant dual 31-tooth star system. Look at the cascading gear sequence on the screen. Step 1 is the primary date indicator. The existing 31-tooth date star, the one that jumps every midnight, acts as the fundamental driver for the entire month mechanism. As it completes its monthly journey, it passes its kinetic energy down the chain. Step 2 is intermediary detection. The primary date star meshes continuously with a second, identical 31-tooth star. Because they have the same tooth count, they both complete exactly one full revolution per month. However, this second star carries a dedicated, extended driving finger. Step 3 is the month-end trigger. As the date star snaps from 31 back to 1 at the end of the month, the driving finger on the second star sweeps around and violently actuates the 12-tooth month star, advancing it into the new month. The 12-tooth star is then locked precisely by its own heavy jumper spring. Please read the mechanical economy note. By utilizing the existing date star as the primary driver, absolutely no new power source is required from the base movement. The second 31-tooth star serves purely as a mechanical 31st-day event detector. It acts as a physical logic gate that only opens once every 31 actuations. Watchmakers are obsessed with efficiency and reducing component counts. So, they asked, do we really need a second 31-tooth star and a separate driving finger? The answer led to the month indication, alternative driving method. Look at the incredible gear component on the screen. This is known as the truncated star concept. Instead of manufacturing a second 31-tooth star and then riveting a separate driving finger onto it, engineers created a single, monolithic component. They took a standard 31-tooth gear and systematically truncated or chopped off 30 of its 31 teeth. As you can see, only one full-height tooth remains on the entire perimeter. This solitary tooth acts as the sole engagement point. The kinematic transformation here is stunning. It elegantly converts the continuous, daily 31-tooth rotation of the date wheel into a single, isolated trigger event. For 30 days of the month, the truncated flat edge spins harmlessly past the 12-tooth month star, touching nothing. But on the 31st day, that single remaining tooth swings around like a baseball bat, striking the 12-tooth star and advancing the month. While it is mechanically much simpler and vastly more robust, it demands perfectly precise, zero-tolerance indexing of the truncated star to the calendar display during initial factory assembly. If it is off by one gear tooth, the month will change on the 2nd or the 30th instead of the 1st. Once the 12-tooth month star is actuated, how is that data presented to the wearer? Let's look at the month indicator, display types. Like the day of the week, we have two primary paradigms. The top image shows the disk-type display. This is a materially identical approach to the day disk. A flat plate, printed with the 12 three-letter abbreviations like JAN, Feb, Mar, is riveted directly to the 12-tooth star. It rotates hidden beneath the dial, revealing the current month through a small rectangular guichet. Because the disk carries no structural load, it is easily swapped for multilingual market variations, from English to French to Mandarin, without altering a single microscopic screw in the underlying mechanical module. The bottom image shows the hand, or needle-type display. Here, a beautifully finished needle is press-fitted to chassis directly to the extended 12-tooth arbor. This format absolutely dominates traditional and heritage designs. The hand indicates the passing months via a sweeping arc over a beautifully printed dial subregister. In high-end Haute Horlogerie pieces, you will often find this subregister crafted from precious metals, featuring deep, sector-engraved typography filled with enamel, elevating a simple indicator into a work of art. We have successfully built a mechanism that tracks the date, the day, and the month. But before we congratulate ourselves, we must confront a devastating engineering reality. This is the important limitation, the simple calendar. Look at the red warning box on the screen. This system suffers from a critical flaw: it is completely, totally physically blind to month length. The problem is that all the mechanisms we have covered thus far rely on a rigid, unyielding 31-day mechanical cycle. The 31-tooth star wheel has exactly 31 teeth. It physically cannot automatically account for the 28 or 29 days of February, or the 30-day months like April, June, September, and November. The consequence of this blindness is highly annoying for the user. At the end of any short month, the calendar will erroneously display the 29th, 30th, or 31st, when the actual Gregorian date is the 1st of the following month. The requirement? This system demands strict, mandatory manual user correction exactly 5 times per year. The user must pull the crown and quickly advance the date wheel past the phantom days to resync the watch. As we look toward the future context of our studies, remember this slide. This specific, highly annoying mechanical limitation is the exact horological problem that the ultra-complex Perpetual calendar, which we will cover in section 9.7, was invented to solve. We are now going to shift our focus from earthly calendars to the heavens. Let's introduce the moon phase indication, the synodic month. To build a mechanical moon phase, we must first understand the astrophysics we are trying to replicate. Look at the astronomical diagram on the screen. The foundation of this complication is the synodic month, or lunaison in French. By definition, this is the exact, observable time it takes for the moon to orbit the Earth and return to the exact same phase, from new moon to the next new moon. But here is where the watchmaker's nightmare begins: the irrational target. The synodic month does not conveniently align with our 24-hour days. It takes exactly 29 days, 12 hours, 44 minutes, and 2.8 seconds. If we convert that into a decimal equivalent, it equals 29.53059 days. Read the horological challenge at the bottom. This 29.53-day period represents the ultimate engineering challenge in simple horology. How do you approximate a complex, irrational, endlessly repeating celestial cycle using finite, whole number, rigid brass gear teeth? You cannot cut a fraction of a gear tooth. Let's see how the old masters solved this impossible puzzle using a brilliant mathematical trick. To solve the 29.53-day problem, watchmakers utilized a brilliant piece of mechanical sleight of hand. Let's examine the moon phase display mechanism concept. Look at the exploded 3D rendering. The blue dial plate sits above a golden gear carrying beautifully rendered lunar discs. The mathematical trick is found in the gear teeth. Instead of trying to create a gear for one single month, they doubled it. They engineered a 59-tooth star wheel. This single wheel handles exactly 2 complete synodic months simultaneously. 59 teeth divided by 2 moons equals exactly 29.5 days per cycle. 29.5 is a very clean, manageable whole number fraction compared to 29.53. Because the gear represents 2 cycles, 2 identical moons must be printed exactly 180 degrees apart on the disc. Now, look at the visual cycle logic. The complex, double-scalloped geometry of the dial aperture, often called a bosom window, is meticulously calibrated. As the 59-tooth disc slowly rotates 1 step per day, the curved edges of the dial aperture act as a physical shadow, organically simulating the waxing and waning effect. It seamlessly transitions from a sliver of a crescent, to a half moon, to a bulging gibbous, to a bright full moon, and back again. It is an optical illusion powered by precise mathematics. If the moon phase disc advances 1 tooth per day, when exactly should that jump happen? This brings us to moon phase actuation timing. Why 1900 hours? Look at the torque draw graph on the screen. It plots power draw against time of day. The green line represents the moon phase actuation, peaking at 1900 hours. The blue line represents the date and day actuation, peaking at midnight. Why are they separated? Read the power management protocol. The critical design protocol dictates that the moon phase is advanced once daily, at approximately 1900 hours, or 7 p.m. absolutely not at midnight. The danger is catastrophic torque drain. Actuating the heavy day jumper spring, the day jumper spring, and the moon jumper spring simultaneously at exactly 2400 hours forces 3 massive, high-tension actuations in the exact same millisecond. The consequence of this simultaneous firing is a massive instant demand for torque, which creates the massive red spike you see crossed out on the graph. This violently starves the escapement of power, causing a severe drop in the balance wheel's amplitude, which ruins the watch's chronometry and accuracy. The solution is elegant power routing. Stagger the mechanical load safely across the 24-hour cycle. Fire the moon at dinner time, and fire the calendar while the user sleeps. Now let's look at the actual gear routing that executes this 1900 hours jump. This is the moon phase gear train, star wheel method, covered in section 9.5.1 of your textbook. Look at the kinetic diagram on the left. You should instantly recognize the shared paradigm. It utilizes the exact same fundamental drive structure as the date and day trains we've already studied. Power flows from the hour wheel to the driving wheel through an integral finger, which finally strikes the massive 59-tooth moon star. The gear reduction formula remains identical, N4 over N1 equals Z1 over Z2, which equals 1/2. The driving wheel rotates once per 24 hours. The kinematic output is simple, the 59-tooth star advances exactly 1 tooth per day. Therefore, it completes exactly 1 full revolution every 59 days. But I want you to focus on the engineering note at the bottom. 59 days is incredibly close to 2 actual lunar months. 2 times 29.53 equals 59.06 days. That tiny, lingering 0.06 day variance between the 59-day gear and the 59.06 day reality is exactly where the mechanical error originates. Let's quantify that error on the next slide. How accurate is the 59-tooth star wheel? Let's conduct a strict moon phase star wheel accuracy analysis. Look at the mathematical proof block on the screen to understand the cumulative drift. The displayed synodic month provided by our 59-tooth gear is exactly 29.5000 days. However, the true synodic month dictated by celestial mechanics is 29.5306 days. If we subtract the two, we find an error per cycle of 0.0306 days. Let's do the time conversion. 0.0306 days equals exactly 44 minutes and 2.8 seconds per month. That means every single month, the moon phase on the dial is about 44 minutes faster than the actual moon in the sky. If we multiply that by 12 months, we get an annual error of 0.3672 days, which is approximately 8.8 hours per year. Look at the cumulative drift warning timeline. By year 1, you are 9 hours off. By year 3, that accumulated 9-hour error has compounded into approximately 1 full day out of phase. This leads to our critical conclusion: after exactly 3 years of continuous operation, the indicator drifts 1 full day out of sync with the cosmos. At this exact point, manual user intervention, pressing the moon phase corrector by +1 day, is strictly required to restore astronomical accuracy. Despite its 3-year error margin, the 59-tooth star is the absolute dominant method used in simple calendar watches. Let's look at moon phase, the 59-tooth star, in practice to understand its physical reality on the movement plate. Look at the blueprint on the left comparing the 59-tooth moon star to the 31-tooth date wheel. Notice the physical scale implications. The high tooth count of 59T dictates a significantly larger physical diameter than the 31T or 7T stars. This massive footprint heavily dictates the geometry and physical layout of the entire movement. It is usually placed at 6 o'clock because it requires immense radial clearance to avoid colliding with the central hand pinions. If the user has to correct it every 3 years, how do they do it? Let's review the 0-point setting procedure. It is a highly specific ritual. Step 1, the user consults a reliable astronomical lunar calendar. Step 2, they wait for the exact day, and preferably the exact hour, of an astronomical new moon when the sky is dark. Step 3, they advance the manual case corrector with a stylus until the golden moon on the disk is completely hidden behind the central cusp of the dial aperture. Step 4, once set, the autonomous 59-day tracking initiates from this newly calibrated 0-point. It is a beautiful interaction between human observation and mechanical tracking. While a beautiful golden moon appearing in a window is incredibly romantic, it is ultimately just an approximation. What if the user needs precise data? This brings us to the moon age, or l'âge de la lune, indication. Look at the stunningly detailed dial close-up on the screen. Notice the numbered track running along the upper curve of the moon aperture, marked from 0 to 29.5. A standard moon phase aperture only provides comparative data. You can glance at it and say, it looks like a waxing crescent, or it's almost full. However, the addition of a graduated scale transforms this romantic complication into a highly precise data instrument. It allows the user to read exactly which day of the 29.5-day cycle they are currently in. Historically, this was not just for show. Read the historical utility note. Prior to the invention of modern electronic instrumentation, knowing the exact age of the moon was absolutely critical for mariners, navigators, and coastal agriculture. The gravitational pull of the moon dictates the tides. By looking at the moon age scale on their pocket watch, a 19th-century ship captain could mathematically calculate exact tidal shifts and high water marks based entirely on the moon's exact age in days. It was a tool of survival. As we prepare to transition into part 4 of our lecture series, I want to offer you a preview of the absolute pinnacle of lunar mechanics. Let's look at the comparison: star wheel versus gear train moon phase. We have spent this module analyzing the star wheel method. Look at the left column. It uses a 59-tooth direct drive. It generates an error of 44 minutes and 2.8 seconds per month. That translates to 9 hours of error per year, requiring manual correction every 3 years. The complexity is low, making it affordable and robust. Now, look at the gold highlighted column on the right, the gear train method. By utilizing a 135-tooth wheel driven through a series of intermediate pinions, the math changes drastically. The error per month plummets from 44 minutes to a staggering 57.2 seconds. The error per year drops to just 11 minutes. As a result, the manual correction interval skyrockets from 3 years to over 100 years. This is the engineering leap we will cover in our next session. The 135-tooth precision gear train achieves a staggering 46 times increase in accuracy. It virtually eliminates the need for maintenance within a human lifetime, elevating a standard complication into the highest echelon of precision horology. We will deconstruct the math behind this 135-tooth miracle in part 4. We have reached the conclusion of part 3. Let's review our summary and key takeaways before we adjourn. We have successfully expanded our calendar beyond the 31-day date wheel. First, we mastered the day of week indication. We learned it utilizes a 7-tooth star architecture. It shares the identical fundamental gear train kinematics as the date wheel, and to ensure synchronization, its actuation safely triggers simultaneously at midnight. Second, we explored the month indication. We saw how it utilizes a 12-tooth star, brilliantly driven by a secondary 31-tooth intermediary star acting as an event trigger. It advances exactly 1 tooth per month. But we also identified its critical flaw: it is totally blind to month length, requiring manual user correction 5 times per year. Finally, we unveiled the moon phase using the star method. It utilizes a massive 59-tooth double moon star. We learned the critical power management rule of staggering its actuation offset to 1900 hours to protect the balance wheel's amplitude from crashing. And we calculated its inherent 3-year drift. You now understand the isolated mechanics of every single calendar display. Coming up in Part 4, we will dive into the math of high-precision 135-tooth moon gear trains, and finally, we will combine every single one of these isolated modules into the magnificent, unified architecture of the complete simple calendar assembly. Thank you for your focus today, and I will see you in Part 4. Welcome back to the lecture hall, everyone, and please take your seats as we begin Part 4 of our deep dive into calendar mechanisms. In Part 3, we successfully expanded our horological toolkit beyond the simple 31-day date wheel. We learned how to mathematically and mechanically track the 7-day week, the 12-month year, and the 29.5-day synodic lunar cycle using isolated star wheel assemblies. However, we ended our last session by acknowledging 2 profound engineering limitations. First, the 59-tooth star wheel moon phase is inherently inaccurate, drifting a full day out of phase every 3 years. Second, all of these isolated displays, date, day, month, and moon, are completely blind to each other. They operate independently, meaning the watch has absolutely no concept of a 28-day February or a 30-day November. Today, we are going to solve the first problem and physically build the second. Our core concept for this module is transitioning from individual, isolated displays to an integrated, modular calendar system driven by a singular 24-hour power source. First, we will mathematically prove the genius of the high-precision lunar kinematics, replacing the 59-tooth star with a 135-tooth reduction gear train to achieve over a century of accuracy. Then, we will undertake a massive architectural synthesis. We will define and construct a quantum simple, or simple calendar, a comprehensive mechanical module indicating day, date, month, and moon phase. We will trace the kinetic power flow through all 23 components of a real-world Dubois-Diprez module. Let's begin by returning to the cosmos. Before we look at the mechanical solution, let's review the astronomical problem we are trying to solve. Please look at the horological blueprint on the screen, the astronomical challenge and the limits of the 59-tooth star. On the left, we have the reality. The true synodic month, the exact time from one new moon to the next, is 29.53059 days. But the 59-tooth approximation we studied in Part 3 assumes exactly 29.5000 days per cycle, because 59 teeth divided by 2 moons is exactly 29.5. Now, look at the error graph on the right. This plots the accumulated error in days against a timeline in months. Notice the steep, aggressive slope of that line. Because of that tiny 0.03 day difference between reality and the machine, the 59-tooth star generates an error rate of 44 minutes and 2.8 seconds every single month. That compounds to an annual drift of nearly 9 hours per year. Look at the red dotted line representing the correction threshold. After exactly 36 months, or 3 years of continuous operation, the mechanism crosses the 1.0 day mark. It has accumulated a full 1-day error, requiring a mandatory, annoying manual intervention from the user. The solution to this unacceptable drift is introducing a compound gear train to approximate irrational astronomical periods with whole number teeth, a brilliant mathematical method borrowed directly from the precision astronomical clocks of the 17th century. Let's dissect the physical mechanics of this solution. Look closely at the architecture of the 135-tooth transmission on the screen. We are replacing a single, direct-drive star wheel with a sophisticated, multi-stage reduction gear train. Let's trace the sequential power path. It begins exactly the same way as our standard calendar. Component 1, the base hour wheel, meshes with Component 2, the driving wheel. Once a day, the integral driving finger, Component 3, actuates component 4, which is a 7-tooth intermediate star. This star advances exactly once daily. But here is where the architecture changes completely. Instead of carrying a disc, the 7-tooth star has a 16-tooth pinion, component 5, rigidly mounted to its arbor. As the star turns, this pinion meshes with component 6, a 16-tooth idler pinion. Finally, this idler drives component 7, the massive 135-tooth moon phase wheel, which serves as the primary display disc carrying the 2 golden moons. Please read the kinematic callout at the bottom. What is the purpose of component 6, the idler? Because it has 16 teeth and meshes with another 16-tooth pinion, it contributes absolutely zero gear ratio change. The ratio is 1:1. It functions exclusively as a mechanical idler to reverse the direction of rotation, ensuring the 135-tooth moon disc tracks astronomically correctly relative to the shape of the dial aperture. Without it, the moon would appear to orbit backward. Now, let's look at the beautiful mathematics behind this arrangement. I want you to follow the mathematical proof of the 135-tooth gear ratio step by step on the blueprint. We are going to prove why this specific combination of gear teeth creates near-perfect astronomical alignment. Step 1. Determine the daily advance rate of the primary driver. We know the 7-tooth primary star advances exactly 1 tooth per day. Therefore, its rotation rate is 1/7 of a revolution per day. Step 2. Calculate the gear train ratio. We trace the drive path. The 16T pinion drives the 16T idler, which drives the 135T moonwheel. The transmission ratio formula is driven over driver. So, it's 16/16 times 16/135. The 16/16 cancels out, leaving us with a final reduction ratio of 16/135. Step 3. Calculate the displayed synodic month. To find how much the massive moonwheel advances per day, we multiply the daily advance rate by the gear train ratio, 1/7, multiplied by 16/135 equals 16/945 ths of a revolution per day. To find the total days per complete revolution, we invert that fraction. 945 divided by 16 equals exactly 59.0625 days. Step 4. The final cycle. Remember, we print 2 moons on the display disc. So we divide the total revolution time by 2. One cycle equals 59.0625 divided by 2, which gives us exactly 29.53125 days. We have successfully used whole number gear teeth to approximate an incredibly long, irrational decimal. We have our theoretical number, 29.53125 days. What does that actually mean for the wearer? Let's conduct an error analysis and evaluate the system longevity of this 135-tooth train. Look at the blueprint on the screen. In the mathematical delta box, we compare our machine to the cosmos. Our displayed month is 29.53125 days. The true synodic month is 29.53059 days. If we subtract them, our mathematical error is an incredibly microscopic 0.00066 days per month. Let's translate that into real-world chronometry. 0.00066 days equals exactly 57.2 seconds per month error. Compared to the 44-minute error of the 59-tooth star, this is a staggering achievement. If we multiply that by 12, the annual drift is a mere 11 minutes and 26 seconds per year. Now, look at the system longevity impact at the bottom. When does the user finally have to push the corrector button? To accumulate a one-day error, it takes 86,400 seconds. If we divide that by our monthly error, we find the correction threshold. The mechanism requires approximately 122.5 to 125 years of continuous, unbroken operation to accumulate a single one-day error. The takeaway is profound. This compound gearing complication transforms the moon phase from a delicate system requiring regular manual maintenance every 3 years, into a functionally permanent, maintenance-free display that will outlast the lifetime of the wearer. To finalize our understanding of lunar mechanics, let's review the diagnostic matrix, evaluating moon phase methodologies. This matrix allows watchmakers to decide which system to utilize based on the specific constraints of the caliber they are designing. Comparing the 59-tooth star method against the 135-tooth gear train method. The star interface changes from a direct 59-tooth drive to a 7-tooth intermediate drive. The transmission upgrades from absolutely none, direct drive, to a 3-stage compound train, 16T plus 16T plus 135T. The displayed month accuracy leaps from 29.5000 days to 29.53125 days. The error per month plummets from 44 minutes to a mere 57.2 seconds. Consequently, the correction interval explodes from an annoying 3 years to an astonishing 125 years. However, look at the bottom 2 rows. The complexity increases from low to moderate, requiring precise depthing of 3 extra microscopic pinions. And naturally, the manufacturing and assembly cost rises from lower to higher. Please read the synthesis takeaway. The 135-tooth architecture represents an astonishing 46 times increase in mathematical accuracy. It elevates a standard, romantic calendar complication into the absolute highest echelon of precision horology. This is why you will see the 135-tooth train exclusively in grand complications and ultra-high-end perpetual calendars. We have now mastered the individual components. It is time to build a watch. We are entering the realm of the simple calendar paradigm, or quantum simple. Look at the defining blueprint on the screen. Under System Capabilities on the left, we can define a simple calendar as a highly complex mechanical module that simultaneously indicates 4 critical dimensions of time: the day of the week, jour, the date, quantum, the month, mois, and the moon phase, phases de la lune. It is a comprehensive snapshot of the temporal moment. However, look at the fundamental limitation on the right. Despite having all these gears and displays interconnected, the system is physically blind to Gregorian calendar variations. It completely lacks the mechanical memory required to account for months shorter than 31 days, meaning February's 28 or 29 days, and the 30-day months of April, June, September, and November. Because the machine lacks memory, it requires a human processor. Mandatory user correction is strictly required at the midnight transition of every single short month. The user must manually advance the date past the phantom 31st day to resynchronize the watch. A simple calendar is brilliant, but it is not autonomous. It requires a relationship with its owner to remain accurate. How do manufacturers actually build these highly complex systems efficiently? Let's examine the assembly architecture, specifically the Dubois-Prez module concept. Look at the exploded isometric diagram on the screen. Historically, watchmakers tried to integrate calendar gears directly into the mainplate of the base movement. This was an absolute nightmare for assembly and servicing. The modern solution is module construction. Notice the middle layer, labeled Calendar Module. This is the plaque additionnel, or module plate. The entire, incredibly complex 23-component simple calendar mechanism is built as a self-contained, entirely separate plate. It is assembled, lubricated, and tested completely independently. It is then mounted directly on top of the base movement, sandwiched safely beneath the dial. Look at the kinetic interface note. How does power transfer between these completely separate layers? The base movement's hour wheel is capped by an intermediary 12-hour wheel protruding upward. This single, solitary nodal point transmits absolutely all required power into the module. The manufacturing advantage of this architecture is immense. One universal, perfected calendar module can be adapted to dozens of different base movements from different brands, completely decoupling complication engineering from base caliber design. This modularity is the hidden backbone of the modern Swiss luxury watch industry. Let's dissect this module layer by layer. We are going to deconstruct the Dubois-Prez simple calendar module into 5 distinct subassemblies to understand how 23 components work in perfect harmony. We begin with architecture subassembly 1, the base drive. Look at the schematic on the screen. This subassembly is the sole source of kinetic energy for the entire module. Component 1 is the 12-hour wheel, or rouet 12 hours. It features an identical tooth count to the base movement's hour wheel below it. It acts as the direct energetic bridge between the continuous timekeeping below and the discrete calendar module above. Component 1 meshes directly with Component 2, the 24-hour wheel, or rouet 24 hours. Driven by the 12-hour wheel, it undergoes exactly 1 revolution per 24 hours. This is the primary nodal point for all calendar actuation. Permanently and rigidly attached to the top of the 24-hour wheel is Component 3, the 24-hour driving pin, or doit. It acts as the master actuator for the entire system. Because it rotates once a day, it swings around like a lighthouse beam, striking the respective calendar components, the date, the day, and the moon at precise temporal intervals based entirely on their angular placement around its orbit. One single pin drives 3 separate dimensions of time. Moving outward from the center, we encounter architecture subassembly 2, the date mechanism. Look at the red highlighted components on the schematic. This is the quantime. Component 4 is the 31-tooth date wheel. This is the primary indicator carrying the 1 through 31 numerals. It is struck once a day by our master driving pin. Component 5 is the date jumper, or sautoir. It locks the 31-tooth wheel precisely in position between actuations. This heavy spring is exactly what provides the snappy, satisfying jump you see at midnight. Components 6 and 7 form the manual override mechanism. 6 is the date corrector, and 7 is the corrector spring. This subsystem functions exactly as a mechanical ratchet. When the user presses the external case pusher, it advances the wheel, 6. The spring, 7, immediately returns the corrector to its rest position, and the jumper, 5, firmly holds the new position. It allows the user to rapidly bypass the 31st day without waiting for the slow automatic drive. Sitting adjacent to the date mechanism is architecture subassembly 3, the day of week mechanism. Look at the blue highlighted components on the blueprint. Notice the striking structural similarity to the date mechanism we just reviewed. Component 8 is the 7-tooth day star, or étoile de 7. It is struck once a day by the master driving pin and advances 1 tooth per 24 hours, rotating the disc that displays the day of the week. Component 9 is the day jumper, or sautoir de l'étoile de 7. It secures the 7-tooth star against violent vibrations and shocks, ensuring the printed day is perfectly centered in the dial aperture. Components 10 and 11 form the manual override pusher system, the day corrector and the corrector spring. Because the day and the date often require completely independent setting, for example, if the watch stops on a Tuesday the 14th, but today is Friday the 20th, they utilize separate, completely isolated correctors. You can advance the day without affecting the date, and vice versa. Modularity within modularity. Now we move to the lower half of the module. This is architecture subassembly 4A, the moon phase drive. Look at the cyan highlighted components on the schematic. Component 12 is the 59-tooth moon phase star, or étoile de lune. It is driven indirectly by the 24-hour master pin. I want you to read the engineering note below it. To maintain the ultra-thin profile of the plaque additionnel, the module plate, this specific de Boisty-Prez module utilizes the space-efficient 59-tooth direct star method rather than the bulky 135-tooth high-precision gear train we discussed earlier. Space constraints often dictate mechanical choices. Component 13 is the moon phase jumper, the sautoir, locking the heavy 59-tooth star in place. Components 14 and 15 are the moon corrector and corrector spring. This allows the user to independently manually set the lunar cycle without disturbing the day, date, or time. The user consults a lunar calendar and clicks the pusher until the moon is perfectly aligned. Because the 59-tooth star is located far away from the 6 o'clock position on the dial, we must physically route its kinetic data downward. This is architecture subassembly 4B, moon transmission and display. Look at the cyan components routing power across the plate. Components 16 and 17 are the intermediate return wheel and intermediate wheel. These tiny gears pick up the rotation directly from the 59-tooth star. Components 18, 20, and 19 are the moon bridges and the intermediate gear. This array carefully and precisely routes the kinetic force around the central axis where the massive hour and minute hands sit to deliver power safely to the bottom of the module. It is a kinetic detour. Finally, the power reaches component 21, the moon display wheel, or roue de lune. This is the actual, physical disc carrying the twin printed golden moons. It is situated at the traditional 6 o'clock position, typical for classic moon phase guichets. It rotates completely in sync with the 59-tooth star above, providing the visual interface for the complex mechanics hidden within. Finally, we reach the last and most hierarchically complex component, architecture subassembly 5, the month mechanism. Look at the green highlighted components on the blueprint. Component 22 is the 12-tooth month star, or étoile de 12. I want you to notice a massive structural difference here. Unlike the day and the date stars, the month star does not touch the 24-hour master pin. It is completely isolated from daily actuation. Instead, it is advanced exclusively at month end via a secondary, dedicated pin mounted directly on the 31-tooth date wheel. Component 23 is the month corrector, an independent manual pusher for setting the month indicator if the watch stops. Please read the kinematic note at the bottom. This is a cascaded actuation. Energy flows hierarchically. The 24-hour pin strikes the date wheel. The date wheel rotates for 31 days. On the 31st day, the date wheel strikes the month star. It is a mechanical chain reaction, where the completion of one cycle triggers the initiation of the next. To truly understand how all 23 components work together, we must map the system. Let's review the kinetic power flow and temporal actuation flowchart on the screen. This maps the flow of energy against the passage of time. At the top, we have the input from the base movement hour wheel. It flows down into the 1, 12H wheel, then the 2, 24H wheel, and finally into the E3, master driving pin. This is our power trunk line. Now, look at the three branches below. Node 1, triggered at approximately 1900 hours, the master pin actuates the moon phase star, 21. Node 2, triggered at approximately 2400 hours, midnight, the master pin simultaneously actuates the day star, 8, and the date wheel, 4. Node 3, at the end of the month, we have the month-end cascade, where the date wheel actuates the month star, 22. Read the engineering callout at the bottom. This is amplitude protection. By staggering the mechanical loads, firing the heavy moon jumper at 1900 hours instead of midnight, the design brilliantly prevents a massive, simultaneous torque drain that would severely drop the balance wheel's amplitude and utterly disrupt the watch's timekeeping accuracy. The choreography of actuation is just as important as the gear ratios. We have built a beautiful, functional, simple calendar. But what is it like to actually live with one? Let's examine the simple calendar reality, user intervention heat map. Look at the calendar grid on the screen. The blue boxes, January, March, May, July, August, October, and December, are safe. These are 31-day months. The mechanical 31-tooth wheel perfectly matches the Gregorian calendar. The user does absolutely nothing. But look at the orange boxes, April, June, September, and November. These are 30-day months. Here, we encounter danger. On the night of the 30th, the watch will automatically advance to the 31st. But tomorrow is the 1st. Therefore, a plus 1 day correction is strictly required from the user via the rapid set crown or pusher. Finally, look at the red box, February. This is critical intervention. In a common year, the user must manually advance the date past the 29th, 30th, and 31st, plus 3 days correction. In a leap year, they must advance past the 30th and 31st, plus 2 days correction. Read the total output at the bottom. Because the physical mechanism lacks memory, the human user must serve as the perpetual processing unit, actively performing exactly 5 mandatory manual interventions annually to prevent system drift. This manual intervention burden leads us directly to the pinnacle of horological engineering. Let's define the core difference: simple versus perpetual calendar. Look at the comparison matrix on the screen. On the left, the quantime simple. Its mechanical logic is blind to month length variations. Because of this, it requires mandatory user intervention approximately 5 times per year. It displays day, date, month, and moon phase. In terms of market positioning, it offers high daily utility and is considered an accessible complication tier for most serious collectors. Now look at the right, the quantime perpetual, or perpetual calendar. Its mechanical logic is fully mechanically programmed for absolute 4-year cycles. Because it possesses mechanical memory, it requires zero user intervention, unless the mainspring completely winds down and the watch stops. It displays all the standard indications plus the critical leap year indicator. Because of this astonishing autonomy, its market positioning is elite high horology, commanding a massive, significant price premium over simple calendars. The perpetual calendar is not just a watch, it is a mechanical computer. And in parts 5 and 6 of our lecture series, we are going to dissect the grande bascule and the complex chem systems that make this autonomous computing possible. Before we conclude part 4, I want to provide you with a highly practical tool. This is the Quick Reference Directory, the 23-part architecture, components 1 to 12. This is an exhaustive component listing for WILSDORF calendar module servicing. If you ever plan to service or assemble one of these modules, you must know these components by heart. 1. The 12-hour wheel, our power input. 2. The 24-hour wheel, our reduction gear. 3. The 24-hour pin, our master actuator. 4. The 31-tooth date wheel, highlighted in red to denote the date subsystem. 5. The date jumper, locking the date. 6. The date corrector, for manual advancement. 7. The date corrector spring, returning the pusher. 8. The 7-tooth day star, highlighted in blue to denote the day subsystem. 9. The day jumper. 10. The day corrector. 11. The day corrector spring. 12. The 59-tooth moon phase star, highlighted in cyan to denote the moon subsystem. These first 12 components form the primary drive, actuation, and primary indicators of the simple calendar module. Continuing our practical toolkit, here is the second half of the Quick Reference Directory, the 23-part architecture, components 13 to 23. 13. The moon phase jumper, locking the 59-tooth star. 14. The moon phase corrector. 15. The moon phase corrector spring. 16. The moon intermediate return wheel, routing power downward. 17. The moon intermediate wheel. 18. The moon bridge, providing structural support. 19. The moon intermediate gear. 20. The moon bridge continued. 21. The moon display wheel, the actual disc visible through the dial aperture. 22. The 12-tooth month star, highlighted in green to denote the month subsystem. 23. The month corrector, for manual advancement. This completes the 23-component architecture. Notice the brilliant modularity. By color-coding the subsystems red for date, blue for day, cyan for moon, and green for month, you can visually trace how power flows and how manual corrections are isolated within the complex, overlapping layout of the brass module plate. This is how a master watchmaker visualizes a mechanism before ever picking up a screwdriver. We have reached the end of part 4. Let's review our synthesis, high-precision moon and simple calendar. We have accomplished a tremendous amount today. First, we explored the gear train moon phase, section 9.5.2. We saw how replacing a simple 59-tooth star with a 7-tooth star driving two 16-tooth pinions and a massive 135-tooth moon will transform the accuracy. We achieved a staggering 46 times improvement, dropping the error from 44 minutes a month to just 57.2 seconds. This made the moon phase effectively maintenance-free for roughly 125 years. Second, we synthesized the simple calendar, section 9.6. We saw how WILSDORF integrates the date, day, month, and moon into a brilliant 23-component modular plate driven by a single 24-hour nodal point. But we also confronted its fundamental flaw: its kinetic blindness requires up to 5 manual corrections annually to maintain synchronization. This brings us to the solution at the bottom of the screen. To eliminate manual month-end correction forever, we must grant the mechanism a physical memory. We must build a machine that remembers the length of February. Next, in part 5, we will enter the realm of analog computing. We will explore encoding time, the 48-cam perpetual calendar architecture. We will dissect the grande bascule and see how physical cam depths translate directly into mathematical skip days. Thank you for your exceptional focus, and I will see you in part 5. Welcome back, everyone, to part 5 of our comprehensive exploration of calendar mechanisms. Today, we cross the threshold from standard watchmaking into the realm of high horology and mechanical computing. Please take your seats. In our previous sessions, we mastered the kinematics of the date, day, month, and moon phase. We built a beautiful, fully functional simple calendar. However, we ended part 4 by confronting the simple calendar's fatal flaw: it possesses absolutely no mechanical memory. It is entirely blind to the varying lengths of the months in the Gregorian calendar, requiring the owner to manually advance the date past the phantom 31st day 5 times a year. Today, we are going to solve that problem permanently. We are going to build a machine that remembers. Our focus for this module is the 48-cam perpetual calendar architecture, known in French as the Quantum Perpetual avec cam de 48. This is arguably one of the most prestigious and intellectually dense complications in all of horology. Look at the blueprint on the screen. The key challenge is automating month-length variations and leap years purely mechanically, without a single microchip or battery. The core innovation that makes this possible is a brilliant, multi-armed lever called the Grande Bascule, working in perfect synchronization with a Grand Cliquette mechanism. We are going to dissect how physical geometry, specifically the depth of a notch cut into a brass wheel, can act as a physical read-only memory to control the flow of time. Let's begin. Let's clearly establish what we are trying to achieve. Look at the Perpetual calendar, core definition and promise on the screen. We are comparing the simple calendar on the left with the Perpetual calendar on the right. The simple calendar requires a user manual correction at the end of every short month. If it's February 28th, the watch will roll over to February 29th, then 30th, then 31st. The user must pull the crown and manually advance it to March 1st. Now, look at the Perpetual calendar. The core definition states that a Quantime Perpetual automatically accounts for all month-length variations without any user intervention. This is the zero-intervention promise. It flawlessly handles the 4 variations: 28-day months, common February, 29-day months, leap year February, 30-day months, April, June, September, November, and 31-day months, all others. It will seamlessly jump from February 28th directly to March 1st. To achieve this, the Swiss industry developed 2 primary architectures. Type A is the 48-cam system, or came to 48, which is the focus of Part 5 today. Type B is the 12-cam system, or came to 12, which we will cover in our final module, Part 6. Both systems achieve the exact same zero-intervention result, but they use radically different mechanical approaches to store their 4-year memory. Let's deconstruct the 48-cam system. To build a mechanical memory, we must introduce completely new components to our movement. Let's examine the architecture of the 48-cam system, 6 key innovations. Look at the stunning 3D CAD rendering on the screen. The fundamental problem we are solving is, how do we automatically advance the date indicator more than 1 day at month end when the month is shorter than 31 days? The answer lies in these 6 interconnected parts. Innovation 1 is the Grande Bascule, or multiple lever. This is the central controller and actuator. It is the brain of the operation. Innovation 2 is the Grand Cliquette, or Grand Ratchet. Attached to the Grande Bascule, this is the extra day driver that physically skips the phantom dates at month end. Innovation 3 is the 31-tooth star cam, or it came to 31. This specially shaped cam receives the Grand Cliquette's forceful push to trigger those extra advances. Innovation 4 is the absolute heart of the system, the 48-cam, or it came to 48. This intricately notched disc is the mechanical memory encoding the entire 4-year leap year cycle. Innovation 5 is the 48-wheel and indicator. This massive gear drives the 4-year cycle and provides the visual display on the dial. Finally, Innovation 6 is the 48-wheel driving pin. This tiny component, mounted on the date star, advances the massive 48-cam exactly 1 step every single month. Let's see how these pieces fit into the module. Let's appreciate the sheer component density of what we are building. Look at the comparison schematics on the screen, simple versus perpetual. We are looking at the Dubois-Diprez blueprints. On the left, we have the simple calendar baseline we built in Part 4. It contains 23 numbered components and successfully tracks day, date, month, and moon phase. It is an elegant, relatively spacious layout. Now, look at the Perpetual calendar delta on the right. To achieve autonomy, we must add 7 highly specialized components, numbers 16 through 27 on this specific diagram. We now have 30 total core components performing a continuous 4-year astronomical computation. But here is the mechanical challenge: all 30 of these components must share the exact same physical footprint as the simple calendar. They must fit within the same diameter and roughly the same thickness. Furthermore, they must all tap into the exact same power source, the 24-hour wheel, without stalling the watch. The engineer must manage an exponentially increased friction load and perfectly balance a symphony of high-tension jumper springs. The density of information and mechanics packed into this tiny brass plate is nothing short of miraculous. Let's look closely at the memory chip of this mechanical computer. Here it is, the component that gives the Perpetual calendar its name. Look at the 48 cam, or came to 48, the calendar's memory. This is a piece of read-only memory, ROM, rendered in solid metal. Its function is to serve as the heart of the system, dictating exactly how many days to skip at the end of every month. Its physical structure is a disk divided into exactly 48 circumferential sectors around its edge. Let's look at the cycle duration. One sector equals exactly 1 month. Therefore, one complete revolution of this cam takes exactly 48 months, which is precisely 4 years, one full leap year cycle. But the genius lies in the depth logic. Each of those 48 sectors is machined to one of 4 physical profiles, or depths. Look at the color coding. The raised surface, gray, is for 31-day months. 0 days are skipped. The shallow notch, yellow, is for 30-day months. 1 day is skipped, the 31st. The medium deep notch, orange, is specifically for February in a leap year. 2 days are skipped, the 30th and 31st. Finally, the deep notch, red, is for February in a common year. 3 days are skipped, the 29th, 30th, and 31st. The physical depth of the brass directly controls the flow of time. Let's map out exactly what is encoded onto that brass wheel. This is the 48 cam profile encoding, 4 years of data. Look at the cam depth matrix on the screen. This is the algorithm the watch runs. We have 4 rows representing the 4 years of the leap year cycle. Years 1, 2, and 3 are common years. Year 4 is the leap year. We have 12 columns representing the months from January to December. Look at the pattern. January, March, May, July, August, October, and December all have flat, straight lines. These are the raised surfaces for 31-day months. April, June, September, and November all have shallow dips. These are the shallow notches for 30-day months. Now, look at the critical February column. In Year 1, Year 2, and Year 3, February features a massive, deep plunge. This is the deep notch commanding a 3-day skip. But in Year 4, the pattern breaks. The notch is only medium deep. This tells the mechanism to only skip 2 days, allowing February 29th to exist before jumping to March 1st. Read the core principle at the bottom. This is a pure mechanical translation. The physical depth of the cam directly determines the lever arm length of the grande bascule, which in turn dictates the exact number of gear teeth, meaning days, that the grand cliquette will skip at midnight. Let's see how that lever actually works. To read the cam and execute its commands, we need a highly complex actuator. Enter the grande bascule, 3 simultaneous rolls. Look at the detailed diagram of component 16, the central controller. It looks like a complex piece of modern art, but every curve is mathematically precise. This single, multi-armed lever consolidates multiple discrete gear trains into one unified, incredibly efficient component. Let's examine its 3 simultaneous rolls. Roll 1 is the actuator and day advance. The entire bascule pivots daily on its central axis. The lower end, A, is struck by the 24-hour wheel pin, lifting the entire assembly. As it pivots, end, B, thrusts forward and mechanically drives the 7-tooth day star exactly plus 1 step. Roll 2 is the date advance. At the exact same moment it advances the day, arm, C, thrusts forward and mechanically drives the 31-tooth date star exactly plus 1 step. But roll 3 is the true genius, the cam reader. Look at the top extension, the beak, 18. Between daily actuations, this beak rests physically directly on the outer surface of the 48 cam. It acts as a physical probe, continuously measuring the current month's depth. The depth it falls into determines the starting angle and therefore the leverage for the grand cliquette to perform month-end corrections. Let's put this complex lever into motion. Let's trace the grande bascule, daily operation sequence across the 4 panels on the screen. This entire sequence happens in a matter of hours every single night. Step 1 occurs around 1900 hours. This is the moon phase actuation. The 24-hour wheel driving pin sweeps around and actuates the 59-tooth moon phase star, advancing it plus 1 tooth. The grande bascule is completely untouched during this phase to protect the balance amplitude. Step 2 happens right around midnight. This is the grande bascule actuation. The 24-hour driving pin continues its orbit and violently strikes end, A, of the grande bascule. The massive lever lifts, pivoting on its central axis, X. Instantly, and B pushes the 7-tooth day star forward, +1 day. Simultaneously, arm C pushes the 31-tooth date star forward, +1 day. Step 3 occurs post-midnight. The snapback and reset. As the 24-hour driving pin continues its circular path, it passes and releases end A. With nothing holding it up, the heavy grande bascule spring, 20, violently snaps the entire lever assembly back down to its resting position. Step 4 is the assessment. As the bascule snaps down, its beak, 18, settles back onto the surface of the 48 cam. It physically re-evaluates the depth of the notch for the current month, setting the precise lever arm angle in preparation for the next month-end correction. It is a continuous loop of actuation and assessment. We know the beak reads the depth, but how does that depth translate into skipping days? This is the job of the Grand Cliquette, executing the skip. Look at the diagram highlighting component 17, the large ratchet. The target component for the Grand Cliquette is the 31-tooth star cam, or cam de 31, component 6. This is a specialized, snail-shaped cam mounted rigidly on top of the date star. The function of the Grand Cliquette is to violently advance this date star by extra days at exactly month end. Let's look at the mechanism in the blue box. The Grand Cliquette piggybacks on the Grande bascule. It is carried along for the ride every time the bascule lifts. However, its stroke length, meaning how far it reaches forward to strike the date cam, is entirely, 100% dictated by how deep the bascule's beak sits inside the 48 cam. It is a direct geometric relationship. A deep notch in the 48 cam means the bascule drops very low. This creates a highly aggressive starting angle, resulting in a long stroke for the cliquette. A long stroke means the cliquette sweeps across the date cam and catches multiple gear teeth, forcing the date to skip 2 or 3 days in a single, massive snap. Let's visualize this extreme scenario. Let's walk through the most extreme mechanical correction the watch must perform, month-end correction, 28-day month, common February. Look at the incredibly complex engagement schematic on the screen. The scenario is the night of February 28 transitioning to March 1 in a common year. The cam profile dictates that the beak, 18, rests in the absolute deepest notch of the 48 cam. Because the beak is so low, the lever arm of the Grande bascule is at its maximum angle, providing the absolute longest possible stroke for the cliquette. Let's trace the action at midnight. The 24-hour pin lifts the bascule. Because of the extreme starting angle, the Grand Cliquette, 17, swings forward with massive reach. It forcefully engages the 31 star cam, 6, deep within its snail profile. As the bascule continues to lift, the cliquette violently advances the date star by 3 full days in one continuous, massive snap. It physically forces the date wheel to blur past 29, 30, and 31. Finally, arm C of the bascule finishes the movement, shifting the star from the phantom 31st to the 1st. The blueprint note is critical. The Grand Cliquette is the skipping mechanism. It skips the intermediate dates. Arm C always finishes the movement by shifting 31 to 1. The result? February 28 is automatically, flawlessly followed by March 1, while the owner sleeps soundly, completely unaware of the violent mechanical ballet on their wrist. Now, let's look at the exact opposite scenario, month-end operation, 31-day month. What happens when the watch doesn't need to skip any days? Look at the engagement diagram on the screen. The scenario covers January, March, May, July, August, October, and December. The cam profile dictates that the beak, 18, rides high up on the raised surface, the party plane, of the 48 cam. Because the beak is propped up so high, the lever arm of the Grande bascule is severely restricted. It is at its minimum angle, resulting in the absolute shortest possible stroke for the cliquette. Let's trace the action at midnight. The 24-hour pin lifts the bascule. However, because the bascule is already held so high by the cam, the Grand Cliquette, 17, simply swings through empty space. It physically cannot reach far enough to engage the 31 star cam, 6. It misses completely. Therefore, only arm C engages the star teeth. It advances the date by the standard, boring 1 tooth. The result is a perfectly normal transition from 31 to 1. The mechanism essentially turns off the Grand Cliquette when it isn't needed, simply by changing its starting geometry. To truly appreciate the analog computation, we must compare the intermediate states. Let's examine month-end operation, 30-day and leap year February side by side on the screen. On the left, we have the 30-day months, April, June, September, November. The cam profile is a shallow notch. The lever arm is medium short. At midnight, the grand cliquette swings forward. Because the angle is slightly more aggressive than a 31-day month, the cliquette stroke reaches just far enough to catch exactly 1/2 of the 31 cam. It skips one extra day, the 31st. The result, 30 jumps seamlessly to 1. On the right, we have the rarest event, the 29-day month, leap year February. This notch only appears once every 4 years on the cam. The cam profile is a medium deep notch. The lever arm is medium long. At midnight, the grand cliquette swings forward with a long stroke. It reaches deep into the 31 cam and catches exactly 2 teeth. It skips 2 extra days, the 30th and 31st. The result, 29 jumps seamlessly to 1. Please read the mathematical proportionality note in the center. The genius of this design is that the physical cam depth is directly proportional to the lever arm angle, which is directly proportional to the number of gear teeth caught by the cliquette. It is a flawless, physical embodiment of a mathematical algorithm. We have established that the 48 cam acts as the memory, and the grande bascule reads it. But how does the memory itself advance? How does the watch know a month has passed? Let's examine the 48-wheel system, advancing the memory. Look at the gear train diagram on the screen. The concept is crucial. The 48 cam does not advance daily. It sits perfectly still for 30 days. It advances monthly. Let's trace the drive path. The primary power source for this subsystem is the 31-tooth date star, 5. We know this star completes exactly 1 revolution per month. The actuator is an integrated driving pin, 27, mounted directly on top of the date star. As the date star completes its monthly rotation and snaps from 31 to 1, this pin swings around and violently strikes the massive 48 wheel, 24, advancing it exactly 1 tooth. Let's do the math. The date star completes 1 revolution per month. At month end, pin, 27, strikes and advances the 48 wheel by exactly 1 tooth. Look at the 48 wheel geometry, it has exactly 48 teeth. Therefore, 1 tooth equals 1 month. Therefore, 1 full revolution of the 48 wheel takes exactly 48 months, which is precisely 4 years. The 48 cam, which is permanently riveted to this wheel, is now perfectly synchronized to the Gregorian calendar cycle. The 48 wheel successfully tracks the 4-year cycle deep inside the movement. But how do we communicate this profound achievement to the wearer? We must route this data to the dial. Let's look at power transfer, the 48-month indicator. Look at the vertical stacking diagram on the screen. We start with the 48 wheel, 24, our long-term memory, which we established rotates once every 4 years. Rigidly mounted directly onto the arbor of the 48 wheel is component 25, the intermediate wheel. The transfer of power is elegantly simple. The intermediate wheel, 25, meshes directly with the 48-month indicator wheel, 21. Crucially, these two wheels share the exact same tooth count. They are a 1-to-1 ratio. A 1-to-1 ratio guarantees an identical rotation rate. Therefore, the indicator wheel, 21, also rotates exactly 1 revolution every 4 years. Look at the user interface note on the right. The indicator wheel, 21, carries the visible dial hand. Its sole purpose is to communicate the internal 4-year mechanical tracking to the dial, showing the user their exact position in the 1461-day leap year cycle. When the hand points to the sector labeled 4th year or leap year, the user visually confirms that the deep mechanical memory is correctly aligned to grant them a February 29th. We have built an autonomous mechanical computer. But what happens if the user leaves the watch in a drawer for a week and the mainspring dies? The memory loses synchronization with real-world time. We must provide a way to reboot the system. Let's examine manual overrides, the correctors. Look at the pusher layout on the screen. The purpose of these correctors is to manually reset the calendar if the mainspring unwinds and the watch loses physical synchronization with real time. Let's identify the inputs. Component 14 is the moon phase corrector. It is completely independent. Component 10 is the day corrector. It is also completely independent. Component 19 is a brilliant piece of efficiency, the combined corrector. It simultaneously actuates both star 31, date, and star 7, day, with a single push, allowing rapid syncing of the daily displays. Finally, component 28 is the month corrector. This is the master reset. It adjusts the 4-year cycle by advancing the 48 wheel. Read the design rule at the bottom. Correctors use external pushpieces to actuate the star wheels independently, entirely bypassing the 24-hour driving pin. The user manually forces the gears forward without waiting for the slow, 24-hour automatic drive. However, forcing the master memory cam manually introduces a terrifying risk, which we must address on the next slide. What happens when a user violently forces the 4-year memory cam to spin using a manual pusher? We encounter a massive mechanical hazard. Let's look at manual correction safety, protecting the bascule. Look at the extreme close-up diagram on the screen. Read the danger box on the left. During normal operation, the heavy beak of the grande bascule is jammed downward by a high-tension spring deep into the notches of the 48 cam. If the user forces the 48 cam to rotate manually using the pusher while that beak is jammed in a notch, the immense lateral torque will violently shear the beak off the bascule, or rip the brass teeth off the cam. The watch will be destroyed instantly. We must implement a solution. Enter component 30, the month corrector rocker, or bascule de correcteur de mois. When the user presses the month corrector, 28, the force doesn't just advance the gear. It first pushes the rocker, 30. The rocker acts as a wedge, automatically and forcefully lifting the entire grande bascule upward against its spring tension. This physically extracts the beak, 18, entirely out of the 48 cam notches. With the beak safely lifted out of the way, the cam is then free to rotate safely into the next month without shearing any components. However, read the golden rule at the bottom. Always advance forward. Never push displays backward. These safety rockers only work in one direction. Forcing a perpetual calendar backward will almost certainly result in a catastrophic repair bill. As we conclude part 5, I want you to appreciate the true magnitude of what we have just studied. Let's look at the engineering context, the analog computer. We are going to compare digital logic to physical logic. Look at the comparison on the screen. On the left, we have a simple piece of digital logic, written in code. If month equals 2 and year equals 4, then skip equals 2. Else if month equals 2, then skip equals 3. Else if month in 4, 6, 9, 11, then skip equals 1. A microprocessor executes this in a nanosecond using microscopic transistors. Now look at the physical logic on the right. This is how a watchmaker writes code. The if month equals 2 and year equals 4 statement is permanently encoded as a medium deep notch milled into a brass wheel. The then skip equals 2 execution is performed by a steel beak dropping into that notch, changing a lever arm angle, and forcing a ratchet to grab exactly 2 gear teeth. Read the profound engineering achievements at the bottom. This mechanism performs genuine mechanical computation, evaluating variables algorithmically. It utilizes physical logic gates to apply the correct skip output at precise month-end intervals. It performs state tracking, maintaining an exact positional state within a continuous 1461-day cycle. And it achieves 100% autonomy using pure mechanics, no microprocessors, no batteries. It represents one of the highest ratios of mathematical output to physical component volume in all of mechanical engineering. However, writing code in solid brass is unforgiving. Let's examine engineering precision and the tip-to-tip critical moment. Look at the extreme magnification of the gear engagement on the screen. The brilliant logic we just discussed only works if the machining accuracy is absolute. The 48 cam profile must be milled with microscopic, sub-millimeter tolerances. If a notch is milled even a fraction of a millimeter too deep or too shallow, the lever arm angle changes. If the angle changes, the grand cliquette reaches too far or not far enough, and the watch skips the wrong number of days. A tiny machining error ruins the entire 4-year calculation. Furthermore, we face the nightmare of spring calibration. Look at the force diagram on the right. The heavy downward force of the grande bascule spring must be perfectly, meticulously force balanced against the horizontal pushing force of the grand cliquette spring. If one overpowers the other, the mechanism jams. This culminates in the tip-to-tip critical moment, the summit sur summit. Similar to the semi-instantaneous date mechanism we studied in Part 2, the tip of the grand cliquette must meet the exact tip of the 31-star cam. The forces build in terrifying equilibrium until the threshold is crossed, resulting in a violent, microsecond snap action that perfectly executes the leap year skip. It is a masterpiece of tension and release. Let's step back from the microscopic tolerances and look at the final, finished product. Let's examine a real-world application, the Audemars Piguet module. Look at the stunning photograph of the actual movement plate on the screen. This is what a master watchmaker sees on their bench. Let's identify the visible components we've spent the last hour discussing. At the bottom, you see the massive moon phase display, featuring dual gold moon phases set against a dark night sky. In the center, you can clearly see the star wheels. The 31-tooth date star and the 7-tooth day star are visible, waiting for their midnight actuation. Sweeping majestically across the entire movement is the grande bascule, the elongated, beautifully curved steel arm that controls the entire system. And supporting it all is the precision bridgework, securing the gear arbors against the violent snaps of the jumper springs. But I want you to read the Haute Horlogerie execution note. At this level of watchmaking, it isn't just about the math, it's about the art. Notice that anglage, the perfectly beveled and polished edges on every single steel lever. Notice the perlage, the overlapping circular graining polished into the baseplate. In luxury watchmaking, flawless technical function and breathtaking aesthetic execution are completely inseparable. The machine must be as beautiful as the math it performs. We have reached the end of Part 5. Let's review our Part 5 summary, the 48-cam Perpetual calendar. You have successfully navigated one of the most complex mechanisms in horology. Let's review the core components added versus the simple calendar. We introduced the Grande Bascule, 16, our master controller handling daily actuation, cam reading, and day/date advance. We met the Grand Cliquette, 17, executing the month-end extra date skip. We saw the 31-tooth date cam, 6, receive the cliquette's force. And we explored the 48 cam, 22, and 48 wheel, 24, which provide the 4-year profile memory and advance at 1 tooth per month. Let's review the critical cam depth logic map on the right. This is the algorithm you must memorize. A raised surface indicates a 31-day month, resulting in 0 extra skips. A shallow notch indicates a 30-day month, resulting in 1 extra skip. A medium deep notch indicates a leap year February, resulting in 2 extra skips. A deep notch indicates a common year February, resulting in 3 extra skips. You now understand exactly how a watch automatically calculates a leap year using a 48-month memory wheel. But what if we don't want a massive 4-year dial on the front of our watch? What if we want the month hand to sweep once a year, like a normal calendar? Next up, in Part 6, our final module, we will explore the alternative architecture, the 12-cam Perpetual calendar. We will dissect the ingenious Maltese cross leap year mechanism, and we will conclude with a massive final chapter summary comparing every mechanism we've studied. Thank you for your incredible focus today, and I will see you in Part 6. Welcome to the final session of our Chapter 9 deep dive into calendar mechanisms. Please take your seats. We have come an incredibly long way since we first discussed the simple 1-to-2 gear reduction ratio. Over the last 5 modules, we have meticulously built up our understanding of how a mechanical watch tracks the date, the day, the month, and the moon, culminating in the magnificent 48-cam Perpetual calendar we deconstructed in Part 5. Today, in Part 6, we are going to complete our journey by exploring the second major architectural approach to the Perpetual calendar, the 12-cam Perpetual calendar, or Quantum Perpetual avec cam de 12. While the 48-cam system is an engineering marvel, it forces a very specific aesthetic choice upon the dial designer. The month hand must take 4 full years to complete a single revolution. What if the watchmaker wants the month hand to behave normally and sweep around the dial exactly once a year? To achieve this, we must fundamentally alter how the watch stores its 4-year memory. We will examine the ingenious mechanical solutions developed to solve this problem, specifically focusing on Maltese cross mechanisms. Then, we will conduct a massive comparative analysis of the 12-cam versus the 48-cam architectures. Finally, we will conclude with a master engineering reference, synthesizing every major concept, gear ratio, and safety protocol we have covered throughout the entire chapter. Let's begin our final module. To understand why the 12-cam system was invented, we must look at the dial. Let's examine how display ergonomics drive mechanical architecture. Please direct your attention to the comparison on the screen. On the left, we have the 48 cam architecture we studied in Part 5. Look at the dial layout. The 48 cam merges the month and the leap year indication into a single, unified indicator. Because the mechanical cam completes one revolution every 4 years, the hand on the dial also completes one revolution per 4 years. This requires a very dense dial layout, with 48 individual month markers crammed into a single subdial. While technically brilliant, it can be difficult for the user to read at a quick glance. Now, look at the 12 cam architecture on the right. This layout provides a much more intuitive, traditional annual month rotation. The month hand completes one revolution per 1 year, sweeping past 12 standard month markers. However, because the main hand no longer tracks the 4-year cycle, the watchmaker must provide an isolated 4-year leap year indicator, typically a small subdial with numbers 1, 2, 3, and L or 4. The crucial takeaway is highlighted at the bottom: both mechanical architectures achieve the exact same, identical 400-year Gregorian calendar performance. The precision is identical. The choice between them is driven entirely by how the watch brand wants the user to interact with the dial. The 12 cam prioritizes legibility, but it forces a massive redesign of the hidden mechanics. Let's dissect exactly what changes inside the movement. Look at the 32-component architecture of the 12 cam module on the screen. This is a top-down view of the modified Perpetual calendar plate. First, look at the total module complexity. The 12 cam system utilizes 32 core components, compared to 30 in the 48 cam system. It is slightly more complex. Why? Read the core challenge box. In the 48 cam system, the February 29th notch was simply carved directly into the massive 4-year cam. But the main 12 cam rotates once a year. Therefore, it physically cannot accommodate a February 29th slot, because that day only occurs every 4 years, not every year. If you put a leap year notch on an annual cam, you would have a leap year every single year. This necessitates the addition of component 26, the leap year cam, or cam d'années bisextiles. This is an external mechanical memory bank. It is a separate, specialized cam fixed directly to the 48 wheel, rotating once every 4 years. Because we have a new cam, we must route that data to the new dial indicator. This requires component 27, the intermediate wheel. In this architecture, it is rerouted to drive the isolated leap year indicator on the dial. The 12 cam solves the legibility problem by splitting the mechanical memory into 2 distinct physical locations, an annual cam for the months, and a 4-year cam for the leap year. Let's look closely at the primary cam in this new system. This is component 23, the 12 cam profile and sector logic. Look at the 3D rendering of the cam interacting with the grande bascule beak. Unlike its massive 48 sector cousin, this cam is divided into only 12 sectors. Its rotation cycle is exactly 1 revolution per year, 12 months. The depth logic is identical to what we learned previously, but it only contains 3 depths instead of 4. Depth 1 is the raised surface. The trigger is the 31-day months. The logic dictates minimum lever arm tilt, resulting in 0 days skipped by the grand cliquette. Depth 2 is the shallow notch. The trigger is the 30-day months. The logic dictates moderate lever arm tilt, resulting in 1 day skipped, the 31st. Depth 3 is the deep notch. The trigger is February. The logic dictates maximum lever arm tilt, resulting in 3 days skipped, the 29th, 30th, and 31st. But look at the structural limitation warning at the bottom. Because it completes its cycle annually, there is no dedicated physical sector for a 29-day leap year February. Every February on this cam is a 28-day common February. We must find a way to physically override this deep notch once every 4 years. How do you mechanically override a solid piece of brass? Enter component 26, the leap year override function. This is one of the most brilliant mechanical logic gates in all of horology. Look closely at the incredibly complex dual contact mechanism on the screen. In panel A, years 1, 2, and 3, we see the normal state. The grande bascule now has a second contact tip, in addition to its main beak. While the main beak rides on the 12 cam, this second tip hovers near the leap year cam, component 26, which rotates once every 4 years. During years 1, 2, and 3, the leap year cam presents a normal surface, a deep cutaway. This allows the bascule to tilt fully into the deep February notch of the 12 cam. Result, full bascule tilt, meaning a 3-day skip for a common February. Now look at panel B, year 4. The leap year cam has rotated 90 degrees to present its extended surface. When the main beak tries to drop into the deep February notch of the 12 cam, it can't. The second contact tip hits the extended surface of the leap year cam, physically propping the bascule up. It mechanically reduces the lever arm tilt. Read the dual contact logic at the bottom. The grande bascule simultaneously reads the 12 cam with its beak and the leap year cam with a second tip. The resulting output is the exact geometric sum of both cam profiles. Because the bascule is propped up in year 4, the cliquette stroke is shorter, resulting in only a 2-day skip. February 29th is allowed to exist. To solidify our understanding of these two distinct architectures, let's review the operating principle matrix, 12 cam versus 48 cam. Look at the comparison table on the screen. Let's compare the system parameters. Main cam revolution, the 48 cam takes 4 years, the 12 cam takes 1 year. Main cam sectors, the 48 cam has 48 sectors, the 12 cam has only 12 sectors. Leap year handling, the 48 cam integrates it directly into its profile, the medium deep notch, the 12 cam requires a separate cam, component 26, to override the main cam. Bascule contact points, the 48 cam requires only one, the beak, the 12 cam requires two, the beak plus the second tip. Separate LY indicator, the 48 cam has no separate indicator, the 12 cam has yes, WIL22. But look at the role of the 48 wheel at the bottom. In the 48 cam system, it is the direct cam profile. In the 12 cam system, it serves as the mounts for the LY cam and the month drive. Read the diagnostic rule. While the input drive from the 24-hour wheel and the outputs to the date star are absolutely identical, the internal mechanical architecture for storing 4 years of physical memory fundamentally diverges. The 12 cam is essentially a dual processor system, while the 48 cam is a single, massive monolithic processor. If the main cam in the 12 cam system only rotates once a year, how does it physically connect to the 4-year memory wheel? Let's examine the kinematics and gear reduction in the 12 cam. Look at the gear train layout on the screen. Let's trace the power flow. The 31-tooth star, 5, rotates once a month. Its driving pin, 29, strikes the 48 wheel, 25, once a month. Therefore, the 48 wheel takes 4 years to complete one revolution. This is our 4-year base. But the 12 cam, 23, must rotate once a year. Therefore, it is mounted on a 12 cam pinion, 24, that meshes directly with the 48 wheel, 25. Look at the critical gear ratio box. This is the math that makes the system work. The 48 wheel rotates 1 rev per 4 years. The 12 cam pinion must rotate 1 rev per 1 year. Therefore, the exact gear ratio between them must be 4:1. The 12 cam pinion rotates exactly 4 times faster than the 48 wheel, perfectly converting the 4-year base memory into an annual output for the month hand. Also, note the correction routing on the right. The manual month corrector, 30, bypasses the main train entirely, injecting force directly upon the 12 cam pinion, 24, to advance the months rapidly without waiting for the date wheel to spin. The dual contact bascule we just studied is the modern solution for the 12 cam system. However, there is a much older, highly revered classical method. Let's examine the alternative architecture, the classical Maltese cross. Look at the beautiful, highly symmetrical mechanism on the screen. In this vintage architecture, the WIL1, 12 cam is integrated directly with the 2, 12-tooth month star, rotating exactly once per year. But notice that the 12 cam contains a deep circular recess milled right into its center. Housed inside this recess is the 3 leap year cam. It contains 3 symmetric faces for the non-leap years, and 1 large, extended face for the leap year. Integral with this leap year cam is the V4 Maltese cross. Both of these components pivot completely freely on the central star arbor. The genius of this system is the 5 fixed pin. This pin is press-fitted to the main stationary pivot of the movement. It does not move. Instead, the 12 cam and the Maltese cross orbit around it annually. This creates a famous intermittent motion device adapting the leap year logic into a quarter-turn translation. Let's see how this orbital dance works. Let's put the Maltese cross dynamics into motion and trace the 4-year quarter-turn cycle. Look at the 3 progression panels on the screen. In panel 1, before the jump, we see the month star continuing its continuous annual rotation. The Maltese cross is orbiting around the central axis. As it orbits, it approaches the stationary fixed pin. In panel 2, the translation, the magic happens. The fixed pin perfectly engages the notch walls of the Maltese cross. Because the pin is stationary and the cross is orbiting past it, the pin acts as a wedge, forcing the cross to rotate mechanically on its own axis. In panel 3, after 1 year, the pin has exited the notch. The cross is securely locked exactly 90 degrees from its origin, presenting a completely new face to the bascule. Read the 4-year cycle outcomes at the bottom. For years 1, 2, and 3, the pin forces a 90 degrees rotation. A symmetric, deep face is presented. The February logic equals a 3-day skip. But in year 4, the final 90 degrees rotation completes the 360 degrees cycle. The single large, extended face is presented to the bascule. The February logic changes to a 2-day skip. This mechanism achieves perfectly locked, intermittent rotation without any continuous gearing. It is pure, classical mechanical elegance. Regardless of whether a watch uses the 48 cam, the modern 12 cam, or the classical Maltese cross, they all require manual correction if the watch stops. Let's perform a correction path diagnostics to understand the user interface. Look at the flowcharts on the screen. The top flowchart shows the 48 cam routing path. It is a 5-step process. The user presses the corrector, 28, which drives the pinion, 23, which meshes with the massive 48 wheel, 24, which drives the intermediate wheel, 25, which finally moves the indicator, 21. This requires extensive gear train engagement during manual advance, which can feel heavy and requires careful pusher action. The bottom flowchart shows the 12 cam routing path. It is a highly efficient 2-step process. The corrector, 30, acts directly on the 12 cam pinion, 24. The corrector acts directly on the primary memory cam, offering a far simpler mechanical engagement and a much lighter, crisper feel for the user. However, despite these routing differences, both systems share a universal safety rule at the bottom. Both architectural systems strictly require the grande bascule beak to be mechanically lifted completely off the cams during manual correction to prevent catastrophic shearing of the delicate brass profiles. The pushers must be engineered to lift the bascule before they turn the gear. We have reached the culmination of our technical analysis. Let's review the master diagnostic, calendar mechanism hierarchy. Look at the ultimate comparison table on the screen. This matrix summarizes the entire evolution of calendar horology. The first row is the simple calendar, quantum simple. It successfully displays the date, day, month, and moon. However, it completely lacks leap year capability. Consequently, the manual correction requirement is severe. It requires intervention 5 to 7 times per year at the end of every month shorter than 31 days. The second row is the Perpetual 48 cam. It displays all 4 basic indications, plus it possesses the auto 48 cam leap year capability. Manual correction is only required if the watch stops. The third row is the Perpetual 12 cam. It also displays all 4 basic indications, plus it possesses the auto 12 cam plus leap year cam capability. Manual correction is only required if the watch stops. Read the synthesis note at the bottom. The leap year complication fundamentally shifts the mechanism from a passive display requiring frequent user intervention into a completely autonomous analog computer running a continuous 400-year cycle. It is the defining line between standard watchmaking and haute horlogerie. To truly master this chapter, you must understand the mathematics behind the metal. Let's review the master mathematical reference, gear ratios and errors. Please memorize these formulas. Under date kinematics, we have the 2 methods for achieving the mandatory 24-hour step-down. Method 1, direct drive N2 over N1 equals Z1 over Z2, which must equal 1/2. Method 2, intermediate drive N4 over N1 equals Z1 times Z3 over Z2 times Z4, which must equal 1/2. Under Perpetual 12 cam, we have the critical ratio linking the 4-year memory to the annual display. The 48 wheel to 12 cam pinion ratio must be exactly 4:1. The pinion rotates exactly 4 times faster to convert the 4-year base to an annual output. Finally, under moon phase lunation periods, we see the quest for accuracy against the base synodic target of 29.53125 days. The standard 59-tooth star achieves 29.5 days per cycle, resulting in a massive error of 44 minutes 2.8 seconds per month. The precision 135-tooth train achieves exactly 29.53125 days per cycle. It drops the error to a microscopic 57.2 seconds per month. These formulas are the absolute bedrock of calendar complication engineering. They prove that every gear tooth is a deliberate mathematical choice. If there is one single component that defines the genius of Chapter 9, it is the one on the screen now. Let's review component synthesis, the Grande Bascule masterpiece. Look at the isolated CAD rendering of this extraordinary lever. This single, irregularly shaped piece of steel performs 5 distinct, highly complex tasks simultaneously. 1. Actuator, end A. It receives the daily energy burst from the 24H wheel pin, lifting the entire assembly. 2. Day driver, end B. As it lifts, it mechanically advances the 7-tooth day star. 3. Date driver, arm C. Simultaneously, it mechanically advances the 31-tooth date star. For cam reader, beak between actuations, it rests on the cam surface, reading analog cam depths to determine structural logic. 5. Extra day trigger, grand cliquette based entirely on the lever arm geometry dictated by the beak, it drives the ratchet to skip 0, 1, 2, or 3 days at month end. Read the conclusion at the bottom. The Grande Bascule is self-adjusting analog logic replacing 3 discrete gear trains within a single, unified lever. It is the ultimate expression of mechanical efficiency, replacing hundreds of potential parts with one perfectly machined component. How do these incredibly complex perpetual calendars look when they are finally assembled into a luxury timepiece? Let's look at movement architecture and real-world integration. Look at the breathtaking Breguet caliber on the screen. Read the architectural notes on the left. Perpetual calendars are modularly layered directly over the base movement's 12-hour wheel. This allows manufacturers to utilize their proven, reliable base calibers while adding massive complexity on top. In high horology integration, as seen in these Breguet calibers, master watchmakers often combine the perpetual calendar intimately with equation of time and power reserve mechanisms. They stack complication upon complication. The most astonishing fact is that the master calendar plate adds minimal total height to the watch, while housing up to 32 independent, vertically stacked components. Look at the movement photograph on the bottom right. You can clearly see the day star, 8, the date star, 5, and the beautifully finished Grande Bascule sweeping across the entire module. It is a densely packed city of gears, operating in perfect, silent harmony. To truly understand the perpetual calendar, we must map its entire temporal hierarchy. Let's review the kinematic flowchart, energy routing across timescales. Look at the flow diagram on the screen. The genius of this system is that it operates across 3 distinct timescales simultaneously. The daily cycle triggers at midnight. Power flows from the base movement to the 24H wheel and into the Grande Bascule. The bascule splits the energy, simultaneously actuating the day star and the date star. The monthly cycle relies on the daily cycle to function. The date star completes its 31-day rotation and drives the 48 wheel, plus 1 tooth per month. Simultaneously, the 12 cam advances 1 sector. The 4-year cycle relies on the monthly cycle. The 48 wheel slowly completes its 1 revolution over 48 months. As it turns, it drives the leap year cam into position, and it drives the 4-year indicator on the dial. Read the summary at the bottom. This is a simultaneous routing of mechanical energy scaling from a rapid 24-hour baseline up to a massive 1,461-day complete revolution. It is a cascading hierarchy of power, where the completion of the fast cycle provides the exact kinetic impulse required to advance the slow cycle. While the mathematics are beautiful, the machine is fragile. Humans make mistakes. Therefore, we must review safety by design, user intervention and failsafes. Look at the defensive architecture diagram on the screen. Module 1 is the golden rule. Manual correction of a perpetual calendar is only required if the watch stops completely. If it is running, leave it alone. This prevents synchronization conflicts. Module 2 is the DOIG Tirisort, the spring-loaded finger. It mechanically retracts when overloaded during manual adjustments. It prevents snapped gear teeth when user input conflicts with automatic movement. The spring constant, K equals 0.05 newtons per millimeter, is meticulously calibrated to ensure a failsafe engagement angle greater than 15 degrees. Module 3 is the bascule lifting rocker. Manual correctors physically lift the grande bascule beak completely off the cams before advancing the wheels. This absolutely prevents catastrophic shearing of the delicate analog cam profiles. The pushers must guarantee a minimum clearance of 0.15 mm to protect the complex cam geometries. The machine is designed to survive its owner. To navigate the world of high horology, you must speak its language. Let's review the terminology master glossary. Look at the translation table on the screen. Memorization of this terminology is essential for interaction with original Swiss technical schematics. In Group 1, Indicators and Dates, we have Quantime, date/day of the month, Montercalendrier, calendar watch, Annies bissextiles, leap years, and Lunaisen, synodic month. In Group 2, Core Components, we have the Grande Bascule, multi-lever/grand rocker, the Grand Cliquette, large ratchet, the Cane de 48/12, 48 cam/12 cam, and the Croix de Maltese cross. In Group 3, Mechanics, we have the Sautoir, jumper/click spring, the Deut d'entraînement, driving pin, and the Neuer, recess. If you ever plan to open a Swiss technical manual or speak with a master watchmaker in Geneva, you must know that a jumper spring is a Sautoir and a date is a Quantime. The language is as precise as the mechanics. As we prepare to close this massive chapter, let's distill everything we've learned into the 6 pillars of calendar horology. Look at the 6 fundamental engineering principles on the screen. 1. Gear reduction. Stepping 2 rev/day down to multi-year cycles using precise mathematical ratios. 2. Intermittent motion. Utilizing star wheels and Maltese crosses to convert continuous kinetic flow into discrete, satisfying jumps. 3. Energy storage. Using heavy jumper springs to store hours of kinetic force for a violent, split-second midnight release. 4. Analog computing. Using cam depths to physically encode Gregorian calendar logic via variable if-then mechanics. 5. Lever amplification. Using variable lever arms on the grande bascule to amplify output force dynamically, skipping multiple days instantly. 6. Safety by design. Implementing overload-compliant spring fingers and lifting rockers to protect rigid gear teeth from human error. These 6 pillars are not just watchmaking concepts, they are fundamental principles of mechanical engineering. A perpetual calendar is simply the most elegant, miniaturized application of these pillars ever devised by human hands. Before you can consider yourself proficient in Chapter 9, you must pass the Chapter 9 competency audit. Look at the checklist on the screen. Validate all these competencies before proceeding to module assembly. Can you derive ratio formulas for Method 1, Method 2, and 12 cam pinions? Can you trace base movement power flow to all 4 calendar indicators? Can you calculate synodic error margins for 59-tooth versus 135-tooth trains? Can you explain the 5 simultaneous functions of the grande bascule? Can you map the 48 cam profile depths to discrete skip day outcomes? Can you detail the 4-year Maltese cross translation cycle? Can you differentiate manual correction routing in 48 cam versus 12 cam modules? If you can confidently answer yes to all these questions, you have successfully mastered the theoretical foundation of mechanical calendar systems. You understand the math, the mechanics, and the safety protocols required to build and maintain these extraordinary machines. We have reached the end of Chapter 9. I want to leave you with one final, profound thought on the true nature of what we have studied over these 6 modules. Look at the glowing, intricate movement on the screen. Read the quote on the right. A mechanical perpetual calendar is pre-computation made physical, centuries of astronomical knowledge encoded in geometry and spring force, running without a power source, without electronics, and without user input, for generations. Think about what this tiny brass machine actually does. The complex, irrational rules of the Gregorian calendar are perfectly encoded in physical cam profiles. The detection of a leap year is encoded in the slow, relentless 4-year rotation of a gear. Month-length compensation is encoded in the shifting geometry of a lever arm. It is a monument to human ingenuity. It proves that we can capture the chaotic, irregular movements of the cosmos, distill them into strict mathematics, and carve those mathematics into solid metal to create a machine that outlives its maker. This is the art and science of the perpetual calendar. Thank you all for your incredible dedication throughout this chapter. Class dismissed.